started and discuss kernelCI a little bit, and the focus being on how to do testing on a wide variety of hardware. So I don't have to, in this crowd, I don't have to do the light bulbs to smartwatches to servers, the supercomputers thing. Everybody here knows Linux runs everywhere, so I don't have to do that slide. But what about testing? Where does Linux testing run? Lost both. There we go. So Linux testing runs slightly fewer places than Linux itself runs, as we know well. So what we want to discuss is a little bit about why that is and what we want to do to remedy that. So let's talk a little bit about kind of the landscape of kernel testing. So yeah, go ahead.
So hi, I'm Guillaume Tucker from Collabora. So there's a couple of slides here showing what the current landscape looks like for kernel testing, especially upstream kernel testing. So we have different test suites and frameworks. I mean, I think we've been discussing them already in all the talks, but let's just like to enumerate them. There's a new one, kernel test framework, which I haven't looked too much into, but maybe Kevin can give some input on.
Well, we're going to have a talk on that later today, so I didn't put too much on here.
Right, so stay tuned for that. So these things, Kselftest is being used a little bit in kernelCI, and I mean, syzbot and KUnit and KTF are not, but are potentially things we could be using. But they're listed here to show that why do we have such a variety of tests. So we'll go through all the different things. So Intel has 0-day, and also the response to Linux kernel performance project. But that is mostly targeting Intel x86 platforms. About mainly. And LKFT, the Linaro kernel functional tests, that's mostly running on Linaro member platforms because that's what we know care about. And CKI from Red Hat is mostly running on platforms that run Fedora, although that's been extended now to stable branches, but that's why it started. So in all these cases, some people have are running Linux on some system, and they need to have a test system for that, so they start with something that solves their problem. So that's why there's such a variety of test systems, because there's a variety of cases where Linux is being run. And then you have other types of testing the upstream kernel. Of course, you have developers, so people who contribute to the code, they have to test it, hopefully, to some extent. And then distros. Been done. So basically, the kernel is tested only where where it's being used the most. So there's a lot of bugs everywhere that are being pushed under the carpet in a way, I suppose. And now I'll hand it over to Kevin for this one. So.
Yeah, so this gets to the story behind kernelCI a little bit, and the goal of kernelCI is to actually try and test Linux on the variety of hardware where it actually runs. So like we said, most of the testing is happening on kind of the common architectures or the common distros. But as we all know, there's lots of places where Linux runs, lots of architectures that are very, very, that are not tested very often or not tested at all, except for the 1 or 2 people that are actually hacking on that kernel. So with kernelCI, the goal is to extend that as much as possible. So this is the architectures that we're doing today, and this has almost entirely been donation-based. So when people send us hardware, we add it to the labs, and that's how things have been growing up till now. So we have and this grew a little bit of history for those who don't know anything about kernelCI. The project's about 4 or 5 years old now, I guess, and it grew initially out of the ARM kernel community because the hardware variety in the ARM community is so diverse, right? So. Here we have like 35 different SoC vendors that have chips or boards in the labs right now, and so there's about 200 plus unique pieces of hardware in the lab right now, and that's growing as people add their own labs or send us hardware. So this is just to show kind of how the variety of hardware in the kernel is growing, and this is just for ARM and ARM64. So the blue line is the number of unique platforms that the kernel supports just upstream. Obviously, out of tree, there's tons more of platform support. But just in upstream, ARM plus ARM64, we're approaching 2,000 unique platforms support in the kernel. Right, so the yellow line is 32-bit platforms. The green line is the 64-bit platforms, which are obviously the newer ones that are growing. But, so this is just since 3.0.
So what's the legacy machine? So what's the legacy machine?
So the legacy machines was kind of that predates device tree. So in ARM, there was these board files that you would, to do board support in ARM before device tree, you would do stuff in a board file. And so that's the legacy support. It's the board files that you can see at the beginning of this time frame, that's all there was. And since then, all the growth is happening in device tree.
Kevin, I have another question. So you earlier talked about how not everything was equally well tested.
Yeah.
Are we happy about the testing of those that are well used?
I don't think so. I mean, I think based on the proliferation of kind of CI frameworks and testing stuff going on now, I think that's an indication that people aren't super happy with the testing that's happening. I mean,
given the limited resources we have, shouldn't we be focusing more on, banging away at platforms that are more widely used?
Well, I think the point here is there's already the focus of the current testing is those platforms, but we also want to be able to test all the platforms, right? But I still think the majority of the testing is going to be on the common platforms because just more people have them, and the distros and things are going to be focusing still on those hardware platforms. But the point of kernelCI, at least from the beginning of kernelCI, was to make sure that other platforms are also represented, and we're still not getting anywhere near all. So this slide also shows just in all the architectures that are out there, this tries to capture a little bit of the variety of platforms in all the other architectures. So again, and this is a kind of only one way of looking at the unique pieces of hardware out there. Obviously, this isn't quite fair to x86 because x86 supports all this hardware with one essentially platform support because of the firmware. But this also shows all the other architectures that have multiple platform support. That's
Kevin?
Yes.
Sorry.
Yeah.
Don Zickas here.
Yeah.
Kind of further up to your point, the gentleman in the front there was saying, wouldn't it also make sense for kernelCI to kind of expand its scope a little bit, saying, hey, now we're going to focus on testing, but focusing on technologies that allow other people to bring in their platforms like that to integrate their testing and make it easier, so that way not all the burden is on the CI systems that test all the platforms.
That's right. Yeah.
But make it easy for other hardware vendors to say, hey, I can plug into this system pretty simply.
Yeah, that is the goal, and we'll get to that. But the goal of the project is to kind of make it easier so we don't have to, people don't have to send hardware to all around. You can set up a lab, plug into these kind of frameworks that we're using, and we can do testing on a more and more, just increase the variety of hardware without having to send hardware all over the place. Yeah. You got a question?
Yeah. Mic working? There you go. Thank you. So the previous graph is a little bit deceiving because, I mean, you have DTS files and stuff in there. That doesn't mean, you guys have any measure of how much of it actually still works as part of the testing that you have done so far? Because, I mean, I'm working on Chrome OS team, and we support some ARM boards, and they're very subject to bit rot.
Yeah, so that's a good point. So these are the number of platforms that actually are upstream, whether they actually work or not. We only test, like in the previous slide, we test about 200 of these in kernelCI. But before kernelCI, the number was even lower. And the testing that we're able to do in kernelCI is, as we'll get to, it's not extensive. I mean, a lot of the testing we're doing for the variety of hardware is just, does it actually boot to a shell? I mean, does it boot to a shell? Does it boot to a RAM disk shell? And that's considered a pass. And even the amount of failures you get with that in mainline is actually pretty. So you're right. I mean, a lot of these platforms, I guarantee that a lot of them are not booting in mainline just because nobody's actually testing them.
So one of the problems, do you see this as a problem too, that a lot of these ARM boards, they tend to have, you need a special Gits in some cases, and they have a lot of out-of-tree stuff that it's hard for to get a wide range of testing like some of the common platforms. x86 does get a lot of testing, right? Because even stable releases, when they come out, a lot of people do test, and I test routinely on my x86. But that's not the case for ARM. And do you have, I have kind of some ideas in my head that why that is the case. Having distros not having good support for these things is the main being. Is that your perception as well, or how do we solve that problem?
I would say it's only partly that. I'd say maybe the bigger problem is ARM vendors take a snapshot of whatever they release when Android comes out or something, and they get it upstream, and then they that stays and it evolves out of tree for a while, and then at some point later they'll sync up again. But in the meantime, there's going to be lots of potential time for bit rot and for failure, and so. But now with kernelCI, we've actually caught a lot of that stuff. So when a platform stops working upstream, at least we can report it and say either we're going to disable it or fix the device tree type of thing.
So do you see much, so vendors fixing the problems, or
Yep.
do you, okay.
Not all of them.
So,
I mean, some are
but
more
yeah,
responsive,
some-
but yeah.
right.
The ones that have actually sent us hardware to include in kernelCI, if they send, that's one of the things we say, if we're going to include your boards, we'd like you to, because we can't do all the fixing ourselves either, right?
So how much of the function of bit rotting is, can be directly correlated to the fact that the platform's no longer of interest, whatever that means?
I would say there's definitely some of that. I haven't done the numbers on that to see who no longer cares. There are some platforms there that, I mean, I've had some of these boards in my lab for many years, and sometimes I just realize that you can't buy it, nobody cares about it, the maintainer's long gone, if I can't fix it simply, I'll just unplug it. So there's definitely some of the don't care factor.
Right, so the follow-up at that point is, do we really need that breadth of testing if nobody's using that platform?
Yep. Probably not to the same extent. I mean, but if it's, my philosophy's always been, if it's easy to keep it working, I'll keep it working. If it's not, I'm not gonna spend my own time. And I think most of the lab owners are that way. If it's up to the people that maintain the labs. If you don't want to mess around with the hardware, you don't have to.
So Kevin, I see two aspects of this testing, right? One is obviously to make sure the board works and it is functional. That's one aspect of testing. And of course, if nobody is using the board anymore, or nobody is manufacturing the board anymore, it's less important that that board be validated. That said, each diverse hardware that comes to the table also validates the promise that Linux has that it can run on a variety of platforms. And to the extent the way we have split the architecture specific and the board specific code from the rest, whether that contract is still as well defined and as broad as it needs to be. That testing of some obscure board can bring up some changes that have occurred in the code that is no longer as broad as we thought it was. So in that sense, some such testing is interesting, but not necessarily.
And that was a little bit of the origin story too, because in the ARM community, it's actually, especially at the time, it was much easier to break other platforms unintentionally by doing something on a new platform, and that's the type of stuff that we were not catching initially, but now that type of thing is much easier to catch.
Kevin, there's a question.
Yeah, I can't see the mic, so just speak.
It's me. So, so going back to the in terms of the platform. Sorry, I got preempted a bit, so I forgot my question a bit. But yeah, in terms of platforms that are supported, there are ARM vendors who really care about upstream and basically only ship upstream. So the people who don't care about upstream are mostly focused on the mobile, high-volume consumer stuff. The people who care about upstream are focused on small volume catalog stuff and enterprise. So it's not, you can't just say that universally ARM is not supported upstream and the platforms are all broken. There's this huge out-free patch set. That's true for some of the ones you've heard of, but the Atmels of this world and the STs of this world have tiny BSPs. They're smaller than the Android patch set.
Also, some chips are supported for a long time, like for automotive, when when the product needs to be supported for a long time. So these are typically platforms that make more sense to add.
Yes. And the mobile ones, people are happy to let them bit rot because they have no value after like a year or 2 years or something. You can't sell them, so nobody cares.
Yeah, and I think
on the enterprise side, on the enterprise side, also we're starting to test on ARM64 servers. So that's also something that probably we need. It's closer to the x86 model.
It's the same as the x86 model.
That doesn't necessarily mean that one of these platforms won't be broken, even if you're testing ARM64.
Yeah, I mean, the other point of this slide is to show that the variety of hardware that we have supporting in Linux is not shrinking, it's growing, right? Which I think we all know, but it's pretty obvious that the supporting variety of hardware is a growing problem, not a shrinking problem. Yeah, go ahead.
Question. I know that QEMU can emulate some of the ARM boards. So what % of bugs do you think could have been coded in QEMU instances? Because they're much scalable or reliable, can provide faster.
There are quite a few things we can catch in QEMU, especially the early boot breakage stuff where if the thing just crashes and before it even boots up, those types of things are caught on QEMU. But there's a lot of stuff that QEMU doesn't emulate, especially obviously the variety of drivers and stuff. But again, I don't really have the numbers on what we've caught on QEMU versus what we've caught on actual hardware.
How many breakages affect lots of the boards rather than say just one with this particular driver?
It's mostly specific boards.
Yeah.
Maybe you might get like an like say OMAP might die or something. You might get a platform that dies, but it's mostly an individual board. And if it's a wide breakage, it's very brief.
There was one breakage like a year and a half ago that broke all the ARM platforms.
Yeah,
It
it does happen. But yeah, and unfortunately, QEMU is mostly useful for those because a lot of the individual platform breakages are driver breakages. And QEMU will emulate things working, but it won't emulate if you write to this register slightly wrong, then the system will explode, obviously. So QEMU doesn't catch that sort of stuff. It's rare that it's relatively rare that you'll see a QEMU failure. It's much more common that you'll see a failure on actual hardware from doing something rude to some device.
So overall, how useful would you consider using QEMU as a kind of its first layer before?
I think it's good as a first layer because it can also run quickly. I mean, you can run it in the cloud essentially. You don't have to dispatch these jobs off to actual hardware. So as a first check, I think it's quite useful.
It's useful for testing frameworks in the kernel, like for media subsystem, there's the Vivid driver, so you can test the common parts, the frameworks, without testing individual drivers, and that's good as a first test because if that fails, other drivers are also going to fail because of the framework problem. So it's good to narrow down problems.
And it's super cheap to run as well, so it's if it provides any benefit at all, it's valuable. It's not like it's costing us anything.
Yeah. So just a little bit more about how we're catching, or how we're actually testing the variety of, not just of hardware, but the variety of kernels that are out there. So right now we're pulling in, we're doing all these tests on mainline, next, stable, and the stable queues. A bunch of different subsystem trees. The subsystem maintainers, we track their trees as well as some individual, yeah, go ahead.
So you're picking mainline, next, stable, RC. Yeah. Isn't LTS may be a better choice because so many of the board vendors are on LTS and LTS is just too.
Yeah, that's the stable tree.
So it does include LTS.
Yeah.
Okay.
Yeah. So it's the stable tree for each kernel version. They track all the latest stable. So we're testing all those. Yeah. And the stable RC, for those you don't know, that's before actually a new stable is released. The patches are pushed up there. So Greg is actually looking at kernelCI before he decides whether it's actually stable or not. So. So several maintainer trees and developer trees we track for people that have asked us to add their tree. And so we're also doing a GCC, and we've just recently added Clang support. So Clang works on, right now, that works on x86 and ARM64, but not much else in terms of actual booting.
It doesn't do it. x86 will be there with Clang 9, but they haven't released that yet.
Ah, okay. So that's not even upstream yet.
Yeah, it mostly works on 32-bit ARM. And it definitely works on ARM64.
For ARM64, yeah.
And next version of Clang will work on x86.
So we've been trying the released versions of those, but also like the latest versions of those to test. Yeah.
So the reason you want Clang is PPF tests depend on Clang, right? Is that Kselftest at least? PPF requires Clang.
Yeah.
So you get a coverage for. Is that a consideration for you to add?
I wasn't even aware that required Clang. So
Right.
the request has just become more people want to actually build their kernels with Clang. Like Android is doing all the kernel builds with Clang.
I see. But yeah, if you're running Kselftest and you want to exercise the BPF, you need Clang.
Okay. That's good to know. And then we're doing any def config that's actually checked in upstream for an architecture. We're building that, so we're able to at least report build failures for the several different def configs, some big endian stuff and a few other things. But there's a whole bunch of these different fragments that we can build, and we can add more. Yeah, go ahead on this one.
Yep, so as you know, kernelCI is doing a lot of boot testing, but we are actively working on improving functional testing as well. So we've been running IGT on some platforms, I mean only the DRM KMS side. We've just started doing a few things on GPUs with i915 and some Mali GPUs as well with Panfrost driver, but that's not really, we're not really pushing the results for that yet because there are still some things that we need to improve with the reporting and dealing with test results. But I mean, we've started reporting the EV file to compliance results to the media mailing list from the media tree and from Next, and that's working pretty well. I mean, we caught a couple of issues, and we're running things like suspend and resume on a bunch of platforms, and we're picking a lot of that fails a lot of the time. But again, we're not really reporting the results too well. So sometimes, you know, we would forward something to one key person to try to get it fixed. But we're ramping up the test suites basically, and then at some point we'll get a better way of reporting results and bisecting as well, which is something I'll be talking about a bit later. And USB smoke test, that's another test suite we've made to verify that USB subsystem is working. And we have a few more on the list, but especially we're adding a baseline test which looks at kernel log error messages like based on the level, and then that's something we want to run on all the platforms to improve the, you know, the current boot test basically relies on just being able to log in, but I mean it's all based on Lava. You know, if Lava says yeah you managed to log in, then it's considered a pass, even if there were like kernel errors and everything. As long as you manage to get to a login, it considers it as a pass. So we want to improve that to have a more positive test to say yes, it actually booted without any errors, and so that should be like rolled out pretty soon because it's something we can run on any platform. And data is growing. I guess I'll hand it over to Kevin.
Yeah. So this is as Guillaume just said. I mean, we're doing. All this matrix is expanding. We have compiler versions, multiple trees, multiple def configs, multiple architectures. The dimensions on our matrix just keep growing. So we're actually collecting quite a bit of data, but we're not actually doing a whole lot useful. We have a few targeted email reports for some subsystems and so on. So one of the things we're trying to work on, and we're looking for collaboration as the project is growing, is that this is an area where we really need help. This is really the next step is what we've been collecting this data for years. How do we actually do a better job of analyzing it, doing reporting on it, detecting things, sometimes detecting things prematurely. There's several different things we could do, all sorts of trends. We've been collecting data on the kernel size and boot times and all these types of things that we have all this data, we're not doing stuff with it. So that's one of the areas of collaboration that we're, most of us that have been working on this project are kind of kernel people, not necessarily data analytics people, right? So this is an area where we would love to have some collaboration. So that's one of the areas going forward. Sorry for the bad joke here. I couldn't resist it.
So one of the problems with collecting lots of data, including logs, especially logs are not structured. Right. So you have no idea really what errors you're looking for. And one of the ways I've solved this, or I've attempted to approach this, is by looking at 10,000 logs, sorting all of the messages and getting a count of how often every message shows up, right? And then I can sort of categorize them. So there's the oddball ones that you find, and then there's a bunch that get repeated often, right? Based on the number of times you've booted. So that might be one way of looking at it. But again, the fact that it's not structured, and then you have these quirks, and where hardware doesn't come up quite right that one time, you end up with a lot of weirdness that you can't explain.
Yeah. And especially with the variety of hardware we're tracking, one of the really interesting things is I got this new kind of obscure log. Have I seen this on any other platform at any other time, right? That type of stuff is actually quite interesting to be able to query.
That's an evolution of what I said about checking for error messages in the kernel log. So right now we're like counting, are there any warnings, critical things? But a good next step would be to store the log line as a kind of error signature, basically, and try to see if that comes back again. Like store it as an error that was seen, and then when you get a new test that comes in, you see if that happened before or not. Like dynamically creating a list of errors.
But the problem with the log lines very often is that they're only showing you a symptom, not the cause.
Right.
Right? So, I mean, the symptom is good to report if you're just trying to report it. But ultimately, if you want to try and fix it, you have to figure out what the cause was. And I find that the logs are generally hit and miss on that. It's not that useful.
So if the problem always shows the log, then we can bisect it. But of course, if it doesn't, then that's a problem.
So how much automation do you have here in terms of post-processing the data? If something boots, you declare that as passed.
Yeah.
That's the easy part. If it doesn't boot, what do you do then? What kind of back-end infrastructure do you have for
So if
dealing
it-
with whatever logs or stack traces and things like that that may show up?
Yeah, so you can talk about bisecting because that's the main thing we're doing, I guess.
I have a question about logs. Is that okay?
Stick to logs.
So from what you said, it sounded like currently you just boot and don't actually look at the logs, don't gather logs.
No, we gather the logs and we with the reporting, if it's a failure, you can go and find the logs, or we report
Yeah,
the
that's
logs
what
with.
I remember seeing.
Yeah,
logs. Okay.
the logs are all there. We're just not we're collecting them. We're not doing anything super intelligent with them.
Right.
To, automatic parsing or that stuff. I mean, but we're storing them all for hopefully future use, right?
Right.
Because we know that there's lots of useful things in there that we could do. We just haven't done it yet.
Right. So I do that when my process doesn't scale, of course. I test a few things on one system and then I do look at logs.
Yeah.
I look for criticals and those manual checks. My process. And then also, do you guys enable some of the options like KSAN and debug options, lock dependency checks and all of those?
Yeah, we have one of the not KSAN yet, but we do like the debug. There's a debug option that turns on a handful of debug things, the lock checking and so on. That's one of the fragments that we build. I think we turned that off because that was actually catching a lot of things it was catching more things than we had this ability to actually fix at the time.
So that would be very important.
Yeah.
I mean, that's what I do on my manual testing that I do. I have all of them turned on. It does, that means that you are catching problems.
Yeah.
But that's the whole idea of testing, right?
Yeah.
So to be able to do that. So that would be something I would say would be
It
important.
actually leads to an interesting, that problem leads to an interesting challenge because if you actually are generating more errors and more bugs and stuff than the capacity to fix them, then people start ignoring results, right? Because it's just failures, the same failures over and over again. So you gotta,
right.
You got to be pretty selective about the types of things that you have the capacity to fix. Until the capacity to actually fix these things grows, you can't actually report everything. There's a lot more things we could turn on and find as well. So I think this is part of the whole part of this discussion. Hopefully we can have today and over the conference is just how we're scaling up this kernel testing, because we are reaching a point where we're generating lots more issues than the community has the capacity to fix manually.
So there is a small subset of debug options that would be very important, which is, I find a lot of problems when I turn on KSAN, for example, and then also lock dep analysis.
Just about one thing
Sorry,
about what Kevin has said about when there's a lot of failures. I think the first thing to do is to start reporting new failures.
Yeah.
So we start, and the first time you run a test, you see all these things are failing, and if new things are failing, then you report them actively.
The trouble with LockDep is it's very, very difficult to get anybody to care. Like some people will care, but it's very, very difficult to get a lot of those issues fixed. Just nobody's interested. They're legit. We should report them. I'm just saying. As one of the people who sends a lot of these emails, eventually you get fed up and go, "Yeah, can we turn this build off? It's annoying."
So back to the question of like what happens when a boot actually fails. I mean, the primary thing we're doing right now is we can report the failure, but we can actually bisect these boot failures. So we actually out of automated process that can go back to the lab and do builds and resend the jobs until we find the commit that failed. So that's the primary thing we're doing right now with those.
So now that we're all one big happy family with Microsoft in the fold, there's a lot of art that Microsoft has in terms of dealing with large amounts of data that's coming back from all the Windows endpoints and the way we process the bugs and problems that we have in terms of booting new releases of Windows. Speaking to the Windows folks, they're very happy to share that technology with the Linux group. If you're interested, we could talk about what's being done in the back end in terms of visualizing the data and making sense of the data.
Yeah, we're definitely interested in that. Any help on that?
Yeah, absolutely. I would love to work with you guys on that.
There's another side of not enabling some debug config. For example, if you get silent memory corruption, then you get asserted failures that you can explain. And you can really bisect them as well because they're very flaky. And the same maybe for deadlocks as well.
You can't bisect it very well.
Can't.
You can't bisect, because
so that then you have something, but
unpredictable.
much more expensive to fix.
Yeah.
Well, it's harder to bisect. You need to run several tests and do some stats to see how often it comes back.
What about? Yeah. So I think we're. So this is just a little bit. Some of the stuff we've already talked about. So in terms of what's next for the project? I mean, the big thing that's next is the project is becoming a Linux Foundation project. I know for those of you who were at Plumbers last year, I said the same thing. This year it's actually happening. So we're going
Write it down.
Yeah. So it's going to announce. We'll announce officially in a couple months at the OSS Europe conference. So that's the plan. But leading up to that, the goal is basically collaboration. So that's also why we're here. There's lots of CI efforts going on. We want to just make sure that we're not duplicating effort. We want our testing to be open source and collaborative, just like our kernel development. Right? So some of the stuff I've already talked about. We've been already getting some more compute horsepower to actually be able to do more builds and to be able to do more stuff kind of server side before we actually distribute to the targets. And then there's new developments like the K unit, and there's lots of work going on with fuzzing and stuff right now that we would like to start being able to run those types of tests and include more testing. So that's the gist of what we have. Any more questions or?
Maybe like the last question, we'll move to the next. No? Terrible question. So. All right, not true.
Is there any other way to catch some errors? So that I guess that you just check only whether it boot up or not, or so, something like that. But in many cases, the driver shows some errors, but so we ignore that.
Well, we don't ignore it now. So if the driver is actually reporting errors in the kernel log, we can catch those things. So we're actually capturing logs in the kernel log has different the kernel log has different levels, so we can catch things. If it's actually logged as an error, we'll catch that. But right now we're basically just counting those things, and we can say that the platform booted, but it's got 20 error messages. So that's the type of thing we can capture and report. We're not doing clever analyzing of the logs to detect exactly what happened.
Yeah, so that makes me wonder whether we should define the common practice that's at least this kernel wording or kernel some level must be searched for critical errors.
Yeah, there's definitely, we've noticed already, there's definitely inconsistent use of kernel log levels because
Yeah.
for the first point, even when you boot the kernel, you can't actually see the log levels, right? So it all just comes out together, right? So I mean, most people don't look at log levels; they just do a print K and they're happy, right? Or a dev print K or whatever. So there's definitely, I think, as more automation comes along, we're definitely going to need to be a little more structured on how we decide to log and at what levels and why and so on. So
drivers in general are pretty good about that.
Drivers are getting better, yeah, with some of the helper macros and stuff. Yeah.
One example is for deferred pros. I've seen things from info to critical minutes.
Yeah.
Or the level itself might be wrong, but they're using structure. Right.
Yeah.
I think we need to move to the next,
Okay.
next topic. Thank you.
Awesome. Thank you, guys.
Next talk is you, right?
Hello, so still related to kernelCI. This one is about dealing with complex test suites, which was something we already talked a little bit about. But I've got a small story here to kind of tell you like why we got into this situation of dealing with complex test suites in kernelCI. So I won't spend too much time, but just give some background and then we can discuss things, because I'm more like looking for solutions and what people think here. So once upon a time, there was a little project called kernelCI. As we know, we've just talked about it, but it was about the ARM ecosystem around 2015, doing builds and boots and loads of boots and boots and boots. And at some point, around 2018, we started running automated boot bisections, which was very useful at reporting issues directly to the patch authors. So even if they were not following the kernelCI results, some things were reported to people and they were happy to see that. That would save them some debugging time, and boot failures are almost always considered as something that has to be fixed. So if someone makes a patch that breaks a platform, even if they didn't know about the platform, they normally care about it. If they can't fix it themselves, something will happen. They'll revert a patch or try to get it working again. So that was good. At the same time, we started running more test suites, like we explained in previous slides. But then, what do we do with these results? Like things like IGT can produce a lot of results, and suspend and resume. If we do that on all the platforms, that's hundreds of results as well. So that's where we needed some help. I mean, we started looking at the problem space and how to fix it, but. Yeah, so these are basically the issues. Like I've said, there's a lot of commits, and why we need to bisect is because in Linux Next you have, of course, every day or every time there's a new Linux Next tag, it's completely like rebased, and you get a lot of merges. You can't test every commit in that. So from mailing list or maintainer tree, you could look at every patch on the mailing list or look at every commit on a Git branch because the volume is quite low. But for Linux Next, sometimes you have issues that only show up in Linux Next when you merge two things together. That's the point of Linux Next. And if that happens, the only way to find a commit is really bisection. So, and git bisect only track one result per revision. So when you do git bisect, you tell it whether it was good or bad, old or new, but you can't say test case 1 did 2.5 as a score, and test case 3 did 3.4, and then compare and all that kind of things. So it's not good for like performance unless you manage your own threshold and you try to determine whether it's good or bad, but you need to run a separate bisection for each test case. It can become very complicated when on each revision some test cases will start passing or failing, and if you're dealing with performance, it can, it's a curve, and when do you decide that it's a pass or fail? So that's why it gets really complicated to report, first of all, as what actually started failing, and then to bisect to find which commit actually broke. Because if you just say yesterday's next performance was that, and today's it's that, if there was a drop, it's going to be really hard to find where the drop is coming from. Sometimes it might be obvious if some people know the code really well and they can correlate it instinctively, but it's not easy. So meanwhile, at Intel, around 2015, the EasyBench project was started by Martin Perez, and that's kind of the origin of what is GWP-ASAN now. That was used in automated testing between 2016 and 2018, and now I think GWP-ASAN mostly using CI bug log, which is pretty good at tracking bugs, but it's not doing bisection. So some people are running EasyBench to deal with the results and find narrow down, because it does some bisection for complex test suites, but people are doing this more like on a manual basis. However, it has some very powerful features. So, I mean, it can schedule tests like we do in kernelCI and generate some reports like we do in kernelCI, but also bisect test suites, like I've just explained, with floating point values and multiple numbers of test cases that pass or fail at different points in time. And that's something we don't have in kernelCI, and we really care about. So actually, I did a presentation at FOSDEM in February about when I explained the problem, and Martin Perez was in the room, and we talked about the presentation, and he explained that he had a solution for that. So then so that's, the problem is, the challenge was clear, like, there's a solution in EasyBench for the problem we have in kernelCI, and, well, it's only typing, right? So many keystrokes later, I made this dangerous tool called Scalpel. It's a proof of concept project. And basically I took some bits of EasyBench that just do the bisection. So it's a compressed version, and there's a Git tree here. But that's a proof of concept that has, I've only tested it on some artificial Git trees, but I've shown that it can work with floating point values and tests that change at different rates. And we've agreed at Martin that it was a good idea to have this tool as maybe as a separate Python package. It's written in Python that we could use both in GWP-CI for Intel and kernelCI, and maybe other people could use that to bisect other test suites, like a generic tool that can be more powerful than Git bisect. There are probably things that Git bisect would do better because it's part of Git, but that's a separate class of issues. So here I have not a real demo. I mean, it's kind of an exercise for the reader. The slides are available, so I'm not going to spend too much time looking at it, but right now. But basically, you start with like an artificial history of things here, and you only report these 3 commits. There's foo and bar. There are 2 test results giving some floating point numbers, and they run 3 times to give you some idea of the variance of the test. So you can see that this test went up and down, and it went up on that branch that got merged later. And so you give these 3 inputs, and it will tell you need to test this version with this test, and you need to test this one because it's a merge base. It will detect when there's a merge base. Looking at the Git tree, it imports the Git objects using the libgit with a Python wrapper. And then so you run tests, and it finds more results, and then it says, oh, this is the one commit for that test case that failed. And it finds that this one went up here and down here, so and that's the whole history. I mean, you can look at the detail of that. You can also run it yourself. There's a demo script in the project. There was a link in a previous slide. So that's how I proved that it could work, and it was written as a command line that can be used in kernelCI. So when we have a set of good and bad test results, we can feed that into the program as it currently stands. It's not running now, but we have a test instance for kernelCI where we can try new things, and I'm planning to get that tested. I mean, I did this work like a month ago, but so maybe later this year it will be good to have this started to be tested. And we could also do it with maybe IGT test suites and see if that's something that Intel would be interested to help with. But it is not the end, so what shall we do with this? Like I've said, we can try to integrate it in kernelCI. We might make a generic Python package, like PyBisect or whatever you want to call it. And in kernelCI, also kernelCI, all the steps to build and generate some jobs and submit them, they were like all hard-coded in Jenkins jobs, but now we're moving all that to command lines, so you can run them in a shell, and the Jenkins automation will just be calling these things, so you don't have to use Jenkins, or you could run it in something else if you want to, like Azure pipeline or GitLab CI or whatever you call it. You can, as long as you can call these things and solve the problems of managing resources and running steps in parallel and stuff like that. So anyway, so there's going to be a new command for kernelCI called KCI bisect to run these things. So you could also rerun a bisection locally if you want to do the same thing with more debug options turned on, for example. So every time there's a pass or fail, you can have more information about what's going on. So having a generic tool that can be used across different projects, maybe that's something we would want to do again for other things. For example, there are loads of steps in a CI system like this when you need to detect the source code changes, you need to build, you need to schedule some tests and get the results and then bisect them. So here, if we have a tool for bisection, that's good, and then maybe we could also have tools for the other things that could be used across different CI systems. So maybe having a toolbox where we have other tools like scissors and hammers maybe could be used to solve the other issues. And then what's also needed, so yeah, we need to improve the email reports for that. So it's about finding the right balance between giving enough detail so it's useful, but not having too much noise so it's lost in the noise. That's always very subjective and depends on the workflows of different subsystems. And yeah, there's a lot of things we need to improve on that. But at least if we can, if we can bisect based on the experience we have from boots, being able to bisect and find the commits that cause the problems, that's already like 80% of the work done to get, to instantize people to fix the problem. So yeah, stay tuned, there's more things coming. So some people have mentioned dealing with large test suites, like Microsoft. I know you're dealing with a lot of data. Is that something that you've solved as well in some way? Like how do you detect if you have one, a huge number of changes, how do you find where the problem was?
Well, that's what I was asking earlier, right? What kind of automation you have in place for this? And Microsoft has invested a lot in automating the back end of the telemetry data that we get from every Windows endpoint, right? And so, and speaking to the Windows guys, they're willing to share all the technology, if you will, with open source projects like what you have here. We would like to get together with Kevin and whoever can come to Redmond and get a meeting going in terms of what we have on the Windows side and see what's applicable to Linux platforms in terms of gathering the data and making the data useful down the road. So it's not something I can talk in a few minutes here, but certainly I think it's worth the discussion.
Okay. Yeah, I'm curious if other people than EasyBench and kernelCI have hit the problem and maybe solved it.
Well, to me, these look like places where you generate the data. And there's really a large amount of back-end processing that you would need to put this data through to make the data useful in terms of gating new commits going in, for instance, as well as the release process that you might have, right? So at Microsoft, they actually use this data to stop Windows updates going out, for instance, right? And so there's also a large body of internal users of internal builds of Windows that also generate this data, which also allows us to control how the internal testing of Windows goes on. So we could do something like that on the next side as well.
How much of your tooling is open source?
I'm sorry?
How much of your tooling is open source of the
Zero.
tools? Zero, right, okay.
But
so you can
so that's where we are,
ideas,
right? That's where we are. But we want to actually look at ways of, as more and more Linux workloads run on Azure, right? So I am pretty blind in terms of Linux telemetry coming back from our cloud, whereas on the Windows side, they have rich telemetry that tells them how things are going on. So we're interested in looking at what we can do to collect more information and be able to use that to control how things get deployed.
I'm curious to know if there are other Google folks. What sort of telemetry are you getting from your cloud? Silence. Amazon? Okay. Was worth a shot.
Facebook. Yeah.
I mean, I know Facebook's using, they've talked about PSI in the past to collect data, but I don't know how much of this is really to catch errors versus, hey, some system's slowing down, and we need to fix that.
So I worked for Sony Mobile for a while, and Sony has a lot of telemetry data from their phones, and I would assume that the other phone manufacturers also have a lot of data that they get.
Oh, another interesting group would be, I guess, Tesla. Those guys also collect a lot of information.
They're not going to share it.
We can ask.
So speaking of end-to-end use of the telemetry data, so if somebody is sitting and coding in a file, let's say there's an assert in that particular function, you could actually get information about how many times in the field that assert triggered, right? So as the developer, you will know where the problems are coming in from the field. That kind of end-to-end solution is what Microsoft has on their Windows platforms.
So I can try to answer. Sir, I think your question is a little too general, Deval. And I mean, because Google does collect a lot of information, obviously, right, from browser for Chrome OS in particular.
So let me be more specific.
I can't speak for Android, but in both cases, we do collect user stats when people opt into it. There are usage information that we do collect about it, and we also get crash reports, which is something I want to talk to Kevin about later, and looking at that. So
do we have time to talk about those right now? No.
My point is that there's a lot of information, and I don't think I have the liberty to speak publicly about it.
But let me make it a bit more specific. Let's talk about the telemetry information. For example, what these guys are getting from their Windows system in Azure. Are you getting similar amount of telemetry from, say, GCE as an example?
I don't know anything about Azure, and I'm not working on the cloud, so I can't answer any of that. I can hardly imagine why not. I mean, why wouldn't they collect it?
I think we're talking now about a lot of data, but I think maybe the most challenging problem is to figure out what data to use to test what commits, because right now we are talking about testing the entire kernel or random commits in the kernel towards, and what test do you actually need to test then? If you know what subsystem a commit is about, you can maybe limit the tests to kind of certain.
Yeah, that's true. That's why we're running the visual2 compliance for the media subsystem, and the same way we could run IGT on the DRM tree. But then there are things, like I said about Linux Next. Sometimes one person makes a change in one tree and it's all fine, and there's another change in another tree, it's all fine, and when you merge the two together, then there's a problem. So that's in Linux Next we need to ideally to be running all the things.
Yes, definitely, but at least that's the first iteration you could run, and then maybe narrow down in some way.
So I'm sorry to interrupt here, but we're kind of out of time, so maybe one more question, or maybe one more answer.
So do you ever see your testing be a gate for commits going in? So the testing effort that you have going here, do you see that being the gate for the maintainers to commit the code? So they would wait for you to say, yeah, this thing doesn't regress anything, doesn't break anything, go ahead and...
I don't think the
so
workflow
this is really
will
an
be
after the
changed.
fact kind of a thing.
I mean, maybe for stable branches, like it's already the case for stable releases, that there's a report sent actively by kernelCI replying to the stable queue review. Maybe, if we have more things, if there's an error, report it there. Maybe the stable release will wait until there's something that comes back. But it depends on, maybe some subsystems will be willing to do that. It depends at which pace they're going.
So yeah, I don't see that. Stable, yes, because once commit goes into the main line, that's how it flows, so that makes sense. We do reverse some cases depending on the failure of the cases, but that's not how the development model works.
Also, it depends on the turnaround time.
0-day preamps. Just going in.
Let's continue this discussion later.
It also depends how long it takes. If it takes 12 hours, then
That's the thing,
yeah.
right? So the university is just suite that is small enough.
Yeah.
Didn't you? While this discussion goes on, I guess Dmitry can set up.
I would just add that it's not officially part of the development process, but there are maintainers that actually look at it before they make decisions. So, but it's not a hard gate.
Or find a fix quick enough to get that fix in.
Okay. Thank you very much.
Is there HDMI? What I need.
You're going to be speaking next?
Yeah. Want to make sure.
Sorry. That discussion is starting to get unbounded. That's what but yeah, we should continue talking about it outside.
I'm starting. So hello, my name is Dmitry Vyukov, and I wanted to introduce an idea called GWP-ASAN. So this idea is implemented for user space, but not yet for kernel. So for kernel, it's just something we can do. Right, so we all want to find more bugs, right? And you can ask, but why you have that killing machine by doing more bugs? And the thing is that all bugs are equal, right? There are log depth warnings in the code that you don't care about, and there are bad bugs in your actual production code. And the GWP-ASAN is the answer for this. And the good thing is that you do not need to write tests and do CI and even do fuzzing. So first of all, KSN crash course. So KSN finds use after free, out of bounds, double free. It uses compiler instrumentation. So before each memory access, the compiler instrumentation checks if this memory access is legit or not. And we have 1/8 shadow memory, which keeps track of the state of the actual kernel memory. And we have red zones around heap objects, and we have quarantine for freed objects. And the problem is that this introduces significant slowdown and memory overhead. So there's no way you will use this in production. And there's that idea called electric fence, or also known as page heap or page guard. It's when we allocate a heap object, what we do actually allocate 3 pages, and we protect two of the pages and place object in the middle page. We can also place it at the end. And those protected pages allow us to catch out-of-bounds access. Right, and when we free the object, we also protect the page itself. And this allows us to catch use after freeze. So this is great because this detects bugs, and this doesn't need any instrumentation and can be enabled at runtime. But the problem is that this is really expensive, right? Because for memory, we allocate a whole page for each heap object. And it's also slow because we need to do those mprotects or DTLB flashes or something for each heap allocation free. Yeah, so this also can't work. It's actually even slower than KSN. But what if we use sampling? So if we combine the electric fence with the sampling, so what we do, we just choose one of the n allocations and allocate it in this way with the surrounding pages. And we can choose the sampling rate low, as low as we need to get the CPU overhead to the level that we need, to the level that actually doesn't matter for us. And we can also limit the number of heap objects to control the memory overhead. But the caveat here is that then you want to apply this to a really large set of machines, right? Because if you use sample 1 of million objects on one machine, it's like you don't really test anything. But if you applied it then to million of machines, then you get back your precision. And for the memory layout, we can do actually an interesting thing. We can pre-allocate on a boot fixed number of pages and protect each other page, and then only use that fixed number. So we don't have even the low overhead, we have completely fixed memory overhead. So if you can dedicate 1 megabyte of memory, this gives you 128 such protected objects. We'll also need some meta information to store the allocation free stacks, maybe PEATs, to provide actionable bug reports, but this doesn't affect performance or memory consumption, so it's easy to do. So the current use, we have it implemented in user space in LVM, and it's enabled for the SCUDA hardened memory allocator. And internally at Google, we enable it for all of the tests. And for the tests, we use a slightly more aggressive sampling rate, so there is actually some effect on the CPU, but for testing, it's fine. And we also enable it, it's also enabled in production by default. And in production, we actually use much lower sampling rate so that we get CPU overhead to effectively 0. It's not measurable by any means. And this already found hundreds of bugs that are super critical that actually happen in production on our actual production workloads. And the bugs are auto-filed and so on. So this is a pipeline of finding bugs. For the Chrome, it's now being rolled out, and at this point, I think it's enabled at some of the actual end-user builds. So on some operating systems, you actually get Chrome build with this feature enabled. And it's also finding lots of bugs that are very kind of important and critical, especially for security. And for Android, it's work in progress. We will also want to deploy it for Android devices. Yes, and potential kernel uses. So I see lots. So for example, distribution could enable it for just everybody on all builds. And all of the cloud data and cloud and data centers could enable it on all servers for all kernels. And if you have lots of consumer devices, large base, you could enable it on all of the devices. There's really, I see no reason to not do this. So there's no overhead and no downsides at all. You just get really critical, important bugs from the field. Yeah, there are several interesting implementation aspects. For example, so when we do allocation, we kind of do some quick check and then go to slow pass to actually allocate the protected page. But this check slows down the malloc fast pass. So the question is, can we implement it without slowing down the malloc at all? And I think it's possible. We probably could piggyback on some of the existing slow pass. For example, when we refill a CPU cache, we could only then kind of do even lower rate checking. Then it may need some potential tunables. Maybe you want to enable and disable it at runtime. Maybe you want it to panic or not at runtime. And obviously you want to tune the memory overhead and sampling rate. But the good news is those can be runtime tunables. So I mean boot time tunables. The question is for small device. So how can it be used on small devices? How small device can still use it? And I think even if you can permit several pages, maybe, I don't know, 2 or 4, that still can be useful. Because the thing is that if you have less code and smaller workload, you also have fewer allocation sites. So you actually need kind of slower rate sampling is fine. Because you just have, I don't know, fixed, 100 of kind of mallocs. Yeah, sampling strategy for kernel may need some tuning, and there is no answer what is the right thing to do, because the problem is that if you have any persistent allocations, they deplete this pool, right? We allocate something never free, and now we have less one object, and if we have just 100 of them, we can soon just deplete all of them. And some of the kernels, they see very infrequent reboots. Right, so the question, what do we do? Maybe we don't sample at boot at all, or maybe we just do very low probability during boot, for example, just one object. Or we can start sampling after X uptime only. Oops, sorry. Or maybe we can blacklist some of the slabs because we know that they have long-lived objects. Maybe it's actually not that bad because, say, if you have even a router, you reboot it infrequently, but still people have, and you have, say, hundreds of thousands of devices, still people have power outages, which reboot them. Sometimes they plug them into different sockets, so again, it reboots and so on. So maybe it's actually not that bad in practice. Yes, and volunteers. If anybody is interested, that would be cool. So we do not have immediate plans right now. If nobody does this, we may do it in future, but it's not in our kind of plans. I think it should be relatively easy and fun for anybody experienced in the MM subsystem. Yeah, that's it. Thank you.
Okay. Sorry. Backing up 2 slides. Do you have a way to just, so you said your persistent objects deplete the pool. Seemed like the only persistent object you had was your use after free, or do you have other persistent objects?
No, if it's still allocated. So object allocated to sample it and it's never freed. So now we kind of stuck with checking this object and we don't check anything else. That's the problem. Okay. For free, you protect it for some time, and then you can, after some time, you can decide to unprotect it.
So where does it live right now, the user space side of things?
In LLVM.
So it's a compiler flag, or how does it work?
So it's kind of a plug. It's thing that you can plug into your memory allocator. So internally, we plugged it into tcmalloc, and LLVM we have a library which gives you hooks that you can insert into your malloc, and we inserted them into SCUDA memory allocator, which is also part of the LLVM So if you use CUDA, I don't know, maybe it's even enabled by default, or you need to flip some flag.
I'll just say that I think it's a brilliant idea to have to use a probability like that to be able to test on live systems. So, yeah.
Thank you. Yeah, it's all ideas are trivial in hindsight, but good. Yeah, thank you.
Hold on.
Okay.
So I mean, I think that a good way forward this would be just to plug something into MM right now, even if it's not optimal, even if you have to kill the fast path just to get the ball rolling. Because I don't think that just throwing it out there I don't think anyone will pick it up as a big project to do, especially the MM folks who don't have time for anything apparently. So maybe the way forward will be just to plug it in and make the performance hit much worse than it should be, and then work from there. And I'm wondering if if that's something you're sort of willing to work with someone to do that.
Yes, so initially we could just penalize the fast pass under some configs and use very simple sampling strategy. So what do you mean by I don't want to get into this right now because this also implies that some deployment, right? Just implementing it doesn't make sense. We will need to use it somewhere, and I don't have time for that mainly. But if somebody is willing to send the patch, I'm willing to review it, for example.
So I'm just thinking that start by keeping the patches simple. I mean, I'm sure we could find someone to do that. I can do that. But start by keeping it simple and then build on top of that time, rather than trying to come up with this perfect solution from day one.
Yeah, we don't need perfect solution, but still it's some amount of work, and somebody needs some plan to actually use it as well.
I mean, people use KSAN now. It could be like a dependent option of that. If you enable KSAN, you enable that.
No, it doesn't make sense to enable.
It doesn't make sense, but it's a testing story, just to test those paths. So you enable that with always like the sampling rate of always, basically. And then once you see that working fine, you make the sampling rate configurable, and users can start dropping that. But just to get people using it sort of as a replacement to KSAN, because this is basically KSAN with sampling rate of 100%. Yeah, so KSAN is this with 100% sampling rate, right? Basically.
Yeah, I'm sure you like it will consume too much memory. I'm sure you can do this. It's like literally at least 2 pages per heap object.
Yeah, let's talk about it.
Well, there's all kinds of knobs in the kernel now that are used only in debugging circumstances and are horrible on performance. So don't be afraid to add another one.
This is not this is not a debugging feature. This is what you enable in all of your devices.
Well,
like,
yeah, but
it doesn't make
so don't pitch it that way.
No,
not at first.
Why?
Pitch it as a debugging tool.
Start with debugging.
One way to think about it is like advertising. If you pay for some service and you have advertising, you could have kind of a slight Kazan that gives you the product for slightly less cost or something.
Okay. Question way back.
Who's got a good arm?
I'll walk. I'll come halfway. Here it comes.
I've got a couple of questions. One is, you talked about an allocation pool. What is the benefit of the allocation, of just having the allocations come out of the pool? Is it just to stop it consuming a sort of unlimited amount of memory? Is that the motivation for that idea?
It's not necessary. Yeah, it's not the only way. We can just call the page allocator. So the nice thing, if they're allocated consequently, is that they share guard pages. Because otherwise you need 3, and here you need 2 per object.
That makes
It's also just, I would expect that in most contexts, kind of having fixed memory overhead is a nice property for production. You can say like this literally consumes 1 megabyte at boot. That's it.
Okay.
Yeah, but this can be done perfectly with page allocator or virtual memory.
My other question was, is there a way that this could be made to work with the cache pools? So a whole bunch of interesting allocations are going to come out of cache pools where we're not going to necessarily easily be able to pull it out of a different pool.
I don't have an answer to this. It depends if the code, like if you suddenly give an object from different memory range, will it break or?
Yeah, I'm not sure either. I haven't looked at the cache pool code. I just noticed.
Generally, code should not care, right, if it's just the object on a different page,
fair enough,
rather than on the same slab page. So probably it should work.
There is a problem when you're freeing the whole pool, you have to.
I don't know where you are, so I don't want to throw it randomly.
Yeah, so with cache pools, the problem is that if you have to destroy the whole pool, you have to deal with all the alien objects as well. That's a slow path. You could probably do that, but still, if you get these alien objects on the free list, maybe something will break.
Well, I think it should be possible to implement it so that it doesn't break, because by that time all objects should be freed. So let's say they're protected, and we just unprotect them later. So freeing the KMM cache should not directly affect it, I think.
That's just another example of abstraction. It's just an abstraction on memory allocation. As long as you can implement that, it should be fine.
What do you mean?
To free up. The question that he asked should be. I agree with you. Should be. It's just a matter of having an abstraction layer on top of the allocation.
Well, yes, yeah, definitely. It should be overall. It should be fixable. If we can do this. Okay, thank you again.
Thank you very much.
And Potapenko, I'm gonna talk a little about uninitialized memory in the Linux kernel. 2 years ago, I've presented kernel memory sanitizer, which is a tool to detect uses of uninitialized memory. Just to remind you, it contains a runtime library that maintains the metadata, the state of every bit in the kernel, whether it's initialized or not. And we also use Clang instrumentation to propagate this uninitialized data and detect uses of uninitialized data in conditions, pointed referencing, and if the data is copied to user space or hardware or whatever, then we are also reporting this as an error. So since then, Sasha has removed kmemcheck from the kernel, but kmsan isn't there yet. So the last 20% of the work took a little longer than I expected. Right now, the kernel supports Clang builds, and Clang itself supports kmsan. I've stabilized the compile interfaces, and I've done quite a bit of work in the shadow memory layout, killing all the crashes, adding some interesting features. But there is still some work to do. So right now we're fully integrated with Syscaller. All the new reports are pre-moderated, which means we only report true positives to the upstream developers, unless people at Google beat us to fixing them, like Eric did for maybe half of the reports that kmsan found. So we found around 150 reports so far. The code is at GitHub, and I'm trying to rebase it at least once a month. So still not upstream. A fun fact is that NetBSD has a working kmsan implementation. It turned out to be really easy. So I've put up a Gerrit code review for kmsan. I just need more eyes on it because, yeah, it's a big chunk of code. Most certainly there are ways to do the things I'm doing a lot easier. Like organizing the shadow memory or interacting with print.kak malloc logs. There is a lot of opportunities to deadlock, and a lot of debug configs are also broken for the same reason, because we are getting to deadlocks. And we may also benefit from subsystem maintainers' domain-specific knowledge about where we want to put checks for uninitialized memory, maybe in DMA, in devices, in file I/O, whatever. So I wanted to shock you with some CV information here, but turns out no one is really filing CVs for uninitialized memory. We have some syzbot stats for the past 2 years. Right now there are 42 open bugs and 108 fixed bugs, of which there is a 21 information leak, 2 of them to the USB subsystem. There were 5 KVM bugs, and most of the bugs are in the network subsystem, just because syzbot is really good at finding those. So the top anti-patterns are copying some, yeah.
So the previous slide, you said there aren't very many CVEs being requested. At least for the information leaks, you should have CVEs.
Well,
yeah, no, we're trying not to request CVEs for kernel stuff.
You don't, but the distros do. Because we want to link back saying, hey,
so some distros and some companies do it so that the patch will actually be backported, so it's more like a way to pressure the management to make them dedicate resources for backporting stuff. And we're trying not to fall into that. There's really no clear policy of requesting CVEs for kernel stuff. Greg is working on an alternative, hopefully towards the end of the year, but we don't want to dig ourselves into the CV. For example, people start requesting CVs for stuff that are just jokes, and it's hard to go back and revoke them, and it's a whole mess, and it doesn't work well for a kernel. Another thing.
You said infleak. What about memory corruptions and use of the freeze and out of bounds?
I'm not disagreeing, but
So if you can allocate about 10 people full-time doing this, full security assessment, analysis, triage, and filing CVs, then you're welcome to do so. And this will be this will not increase number of bugs, number of bug fixes, just the keeping track of things and filing CVs.
And that keeping track of things is actually fairly important from
So
the
is it incredibly important so your employer ready to allocate 10 people? So for the answer is that it's not that important, unfortunately.
Yeah, the problem is that one needs to do some analysis of whether the bug is exploitable, whether it's interesting for the developers. And actually, we are finding the bugs earlier than they hit any distros, some of the bugs at least. So maybe we should invest in earlier testing and earlier detection of those bugs instead of investing into CVs. Here it is.
So I guess the question that I should ask is, how often are you finding bugs in pre-release code versus already released code?
Well, I can get to it in a moment.
Okay.
Yes, so here are the top anti-patterns. A lot of people are copying things like struct sockadr, for example, from the user space, but it can be shorter than expected, and then some of the fields get uninitialized, and people treat them as a whole sockadr. The most common one is just allocating a structure and forgetting to fill something and copying it into the user space. This also includes the padding, because padding always contains some uninitialized data. And a lot of people do not check for reading from USB devices whether the read succeeds or not. So this also leads to uninitialized data. So this graph can give you an idea about the bug lifetime. We only have this many bug fixes with the fixes tags, but there are some really old reports, and there are also a lot of newly introduced bugs. So we sometimes see the bugs being reintroduced, and we sometimes see the bugs in a very fresh code.
What was the average lifetime?
Well,
I mean, so let me rephrase. When was the 2005 bug fixed? 2017 or 2019?
Does it really matter? That's like 2 years versus 10 years. I don't really remember. I can look that up. Yes, so most of the bugs are still there. So right now, syzbot only covers maybe 11% of the x86 kernel code, and most of the attractive attack vectors are not covered. So I expect, for example, the remaining networking code to have maybe 200s of bugs that we haven't seen. And most certainly, the wireless stack has real information leaks that don't require any local code to be run. So what do we do with all those bugs piling up? Although initializing everything sounds a bit crazy, this is probably doable, and at least we can try to do that. This serves two purposes. First, we kill all the information leaks. If we initialize the memory with zeros, there is nothing to leak. And if any code depends on uninitialized data, then it will execute deterministically. By the way, Microsoft has started experimenting with this already, and it ships kernels with initialized PODs since last year. So for local variables, there is a bunch of kernel configs that Casecook has handily put up under a common umbrella. And the most interesting one is the init stack call, which is right now only available in Clang. This is something we want to change in the future, and Linus also wants this to change. So any takers for GCC will be willing to help. We've made some performance measurements of initializing all the local data. There are pretty good results, but also some outliers. And I want to emphasize that benchmarking is hard. And for example, the netperf can perform quite good, but it doesn't show you how the rest of the kernel, how the user space applications work with this mitigation. And on the other hand, there are some end-to-end Android benchmarks, for example, for which we see very big variance because it's just hard to write a reliable benchmark. Ideas on how to benchmark the whole system are still welcome.
So how do I read the two lines there?
Sorry?
So you have a line for hex AA initialization and a line for hex 00 initialization. Why would the value make a difference in terms of performance?
Okay, so there are two options. Right now, we only use this one, the initialization with XAA, because the other one is hidden behind a client flag with a really hairy name that no one wants to use. The difference is that obviously it's easier to encode zero constant in ARM and x86. For example, ARM has a dedicated zero register for that.
So do you, in the case of zero, do you pre-allocate all memory fully zeroed out or only specific fields are zeroed out?
That's about the stack. So we insert some code that initializes all the stack objects at the beginning of every function. And of course, we take advantage of the dead store elimination, but Clang is very bad at it. So there is a lot of opportunities to improve the speed up, and we are already doing something to fix that. So another thing that's landing in 5.3 already is the init on alloc and init on free boot time options. They're basically zero initializing all the allocated or all the freed memory objects in page alloc and in the heap. The difference is small, so init on alloc is more cache friendly, and init on free minimizes the lifetime of the sensitive data. And this is somewhat similar to PAX memory sanitize, but PAX memory sanitize disables initialization for certain memory caches, and we don't know whether it's good or bad for performance and for security, so we haven't tried this yet. And I also believe we're a little faster than PAX memory sanitize, maybe not. Yeah, so here are the performance costs. Initializing all the heap objects is obviously more costly than for the stack, but still we can choose to skip some certain memory caches, for example. We just need better understanding of which workflows are important and which when we can trade security for speed. So here is another quote by Linus regarding heap initialization. Enough said. So that's basically it. Thank you for your attention.
Hello, it's me again. And I wanted to give a short update on various things related to syzcolor and syzbot that happened since last year. So syzcolor is an operating system kernel fuzzer that is coverage-guided, input structure-aware, multiple rating system with focus on automation. And then syzbot is automation on top of syzcolor, which can do continuous kernel build and that does bug reporting, bug tracking, and as web dashboard. So far, it reported about 2,300 bugs, and of which 1,500 are fixed, and approximately 750 are still open. And when I looked several weeks ago, bugs were precisely 2/3 of the reported bugs. So it makes it 3 bugs per day, 2 of which are fixed for 2 years. And some people ask, like, is it getting better? Is there any positive dynamics? And on the graph, you can see number of bugs reported per month for the last year. And on the graph, you can see, actually, I'm not sure what you can see. Like, there's nothing. I can't say that there are any dynamics. The spikes are probably related to either merge windows or that we deployed some bug finding capabilities. But no, it's not getting better. And there's still lots of open bugs and bad bugs, bugs with reproducers, bugs that still happen, that were reported a year ago or more. Okay, so what happened? So first of all, we deployed kmemleak. Kmemleak finds memory leaks. In 3 months, it found 82 leaks, 44 of which are now fixed. And we hit some challenges. So first of all, kmemleak is slow because it scans all of the memory. And we also have some false positives, maybe related to the fact that it doesn't do atomic scan. Maybe it's something else. Nobody actually looked. And some of the reports are very frequent, and some of them seem to be false positives. And also, there's a question of how do you provide reproducers to developers, because memory leaks are completely silent. It's not that you get some splash on the console or something. So what do we do? First of all, we do a scanning only after a batch of tests. So we run several tests and then run scanning. And if there is any leak, then we try to understand which of the tests actually caused the memory leak. So this makes it a bit faster. Then we report memory leaks only if they're reproducible. So this is not true for other types of bugs, but for leaks, what you get is only get one stack trace, which is the allocation stack. So it's not even the stack where kind of the object was forgotten to be freed. So it may not be very actionable without the reproducer. Then we have scanning and the code that talks to kmemleak embed in the C reproducer. So you can actually run them and see the kmemleak report, and you can say test your fix. And then, so how the syzcolor was designed, if it hits any crash, any bug, then it immediately kills the machine and reboots it. So it always works on a clean, on a good state. And this doesn't work well with frequent bugs, especially with false positives. So what we do, if we hit a particular leak, we, again, kill the machine this time, reboot it, but we in the later runs, we start ignoring this particular leak. So the idea is that we hit all of the frequent one initially, and then later we start discovering kind of more interesting and more interesting ones. And for the scanning, we had to do quite tricky dance to fight false positives. So what we do scanning, then we sleep for 4 seconds, then we scan again. Then if we see leaks at that point, we sleep for 1 more second and scan again. And this tends to reduce false positive rate, and there's actually some science behind this. So each of the sleeps and the scans is kind of tied to what the kmemleak does and how it works. Yes, and all of the testing should use kmemleak, because some people even say that leaks are the worst kernel bugs, especially for servers, because they just kind of slowly drain capacity of your servers, and like completely silently nothing happens. Yeah, the next thing is called systematic fault injection. So we added a special mode to fault injection. which works as follows. We have a per thread, per task file, and you can write a particular number to that file. So you write 3. And what this does is this will fold the third allocation, third fold site in this thread after you write this number in this particular task. And then you can read from that file to understand if the fold was injected, if the task has reached that third fold site or it hasn't reached it yet. And what you can do is this, you do the following. So let's say you have a system call. First of all, you inject failure into the first fold site, say first kmalloc. Then next time you re-execute the same test and you inject the fault in the second fault site. Then in the third and so on until you reach the state when the fault wasn't injected. So at that point, you know that you kind of tried all the fault sites one by one and now you kind of tested all of them. So the traditional mode was kind of randomized. So you just fail X% of mallocs, and this doesn't necessarily test all of the sites, and it requires running the test for a long time. And this mode allows to fail each site once with the minimum number of tests, which is pretty cool. Yes, and all of the tests also should use fault injection. And this particularly useful with KMem leak, especially because most common bugs on the error handling paths are double freeze and memory leaks. And I think it should be possible with ptrace in the testing context. So you say you run a test, you check the exit status that is 0, so the test succeeded, and then you run the same test with this fault injection mode using, say, ptrace, and you systematically fail each malloc in each of the system calls in the test. Right, but at this mode, you ignore the exit status because the test will probably fail, but it doesn't matter. We're just looking for the kernel bugs. Yes, and if the kernel code is kind of poorly tested, then the error paths are just virgin lands. I'm not sure what testing they got, if at all. So the next tool was KMSAN, was already mentioned. It uses of initialized values. We found about 220 bugs at this point. 100 is fixed, and we're finding info leaks to user space, including, say, 100 bytes info leak in a wait system call, which is reachable by any user, or info leaks to the USB cables, or use of initialized values in the networking paths or in the security modules. Then we started doing USB fuzzing, and the idea is to stress the kernel from the external side, from the side of the USB cable. Actually, from both sides. So the same test can both kind of do the external workload and call some ioctls. So actually stress kernel from both sides. For this, we added a special debugfs interface, which kind of allows us to inject USB packets in a way that is suitable for fuzzing. And so far, we found about 250 bugs. 100 is fixed, but we know that we just barely scratching the surface, because just for the USB IDs, we have 8,400 of them. And there are interfaces, there are generic interfaces. There are also interfaces per device class, and there are interfaces per device driver. So there's just tremendous amounts of code.
Do you actually need an external USB device to test it, or can you just emulate one? Is there like a software?
This is all emulated in software using this debugfs interface. Yes, it's all driven from a test. Basically, you write to a particular file, a packet, and it's injected. Yes, it's like a tuned device for USB. Yeah, and then we deployed bisection, which is yay. Lots of people ask for it, but fortunately, success rate is about 50%. And when I worked on the bisection, I discovered lots of interesting things. So going back in time is very amusing. So first of all, your compiler starts breaking. Then you take an older one. It's also start breaking with something. Then the older one breaks as well. At some point, your Perl breaks. At some point, your make breaks. At some point, your binutils may break. At some point, there were no old def config, so if you naively used it in your bisection script, sorry, it doesn't exist. Yes, and it's not that you can take just the older versions and they will build the new kernel, obviously. So what you need is for each tool, you need kind of some range of kernels where this particular version works. And then you need to combine like right version of GCC, make, Perl, binutils to kind of do something that can build this particular version. And obviously this will not work with just any glibc as well.
So maybe an option for that is to use something like Yocto, which sort of builds its own environment, and you can go back in time with Yocto to like sort of jump to older kernels with that. Because it does build everything, like all the dependencies, and it did work back at the time. So maybe,
have you tried it?
Not for this purpose, but I mean, I don't see why it wouldn't work, because it does build GCC, it builds Perl, it builds all of that. So to work with that all the
time. For now, actually, we stopped at a pretty recent GCC version, which is 4.1, because of those reasons and number of other reasons as well. So, and for that, we just need 3 GCC versions. So we just switch the GCCs according to, again, to some ranges. Okay, then as you go back, say there is no KSN, no logdep, or KSN loses some of its abilities. So if you track in KSN back, like you can bisect it to basically addition of KSN, for example. And then we see lots of build breakages, boot breakages, and runtime breakages, even under release stacks. So what we do, first of all, we check the releases to find the initial range for bisection, and it happens that lots of them actually build broken or boot broken. So what we have to do, as we go back on a particular release, we have to disable a particular config, and we have lots of those rules just to fix major breakages, because otherwise there's just no way we can do any bisection beyond that release. And actually it starts from very recent kernels. Yeah, so when we deployed it and started reporting results, people started complaining. And so I had to analyze kind of initial results just to understand what happens, what are the root causes, if we can do anything. So I looked at the 118 bisections. As I said, success rate was about 50%. And it turned out that 46% of those were affected by the fact that the bug is racy, flaky, or hard to reproduce. And the thing with the bisection is that you need to answer yes or no 15 times. And if you answer it once wrong, like everything is totally wrong. It's not that you can be like 90% correct. You're either 100% correct or you're 0% correct. Also, actually, this is the major cause. 66% were affected by other bugs. So we just chasing one bug, but then we hit another one. And it's not, some people ask, like, if you can say if it's the same bug or not, but it's not really possible. Partially because more than half of the bug itself has multiple manifestations, either in space or in time. And then even if you can say that this is a different bug, still, what does it mean? Does it mean that the original bug is not there, or it's still there, but you just hit another one earlier? Like you still can do anything useful. And 40% were built or boot broken. We do skip, but those 40% were kind of bisected to the broken range, so we couldn't even, so git bisect skip didn't help. And 8% were bisected to release tags because we disable configs. So that was actually a bug in the config that we had to disable. Yeah, but the light in the end of the tunnel is that when I looked at just the 4 latest releases, it turned out that the success rate is 70%. So if you just bisect in a smaller recent range, it seems to be that there is strong correlation with correct results. Yeah, so before we did it, lots of people asked, why didn't you just bisect it to say, give us the commit that introduced it, or CC the right people? So please never use the word just and bisect in the kernel context, okay? Thank you. So it's far from being just. And the next thing we're working on now is fixed bisections, work in progress. So what we want to do if we have a crash that didn't happen for X days, maybe it's fixed already. So what we want to do, we want to test it on the head. And then if the crash still happens, we want to, so if it doesn't happen, we want to try to bisect to find the fixing commit, and then say to developers that, hey, this is probably fixed by this commit, and if it can make sense, then please close the bug. Or if the crash actually happens on the head, then this may be the right time to send the ping with a new report on the latest commit. And actually, initial results are that we see lots of cases where we had a reproducer that stopped happening, say, 1.5 years ago, and then we tested on head, and it still happened, like it causes the same crash. So for some reason, it just the system kind of unlearned how to trigger it, but the bug is very much there. Yeah, there are also lots of other work, which is probably not very interesting. Coverage. So lots of people ask, what is the coverage? Like, how good it is for my subsystem? Is it testing my subsystem? If it's not finding bugs, is it because we're good or we're just not testing it? So if you go to dashboard, you will see this coverage link, which leads you to the coverage report. And if you click it, you will see the kernel file directory structure. And for each directory, you have the kind of % of coverage. And this is kind of this number of basic blocks, which is some substitute for lines of code. So basically, how large is this directory? And if you can expand the directory, you can go deeper, you can expand other directories and kind of see coverage for particular files. And if you click on the file, you will see coverage on this file. So that here, black is covered and red is not covered. So in this case, for example, it's obvious that the fuzzer cannot progress through this first check in the function. And if you know about the subsystem, maybe you know what's required for the fuzzer to what needs to be improved to actually cover this function. Yeah, you can also see those yellow lines, which means partially covered. So here it's like, I think it's a logical AND. One part is covered, another is not. And you'll also see those numbers, which means how many tests cover a particular line. And this may be useful for some analysis. Yes, there are some caveats. So we collect coverage only from the system call itself, only from this particular task. So we don't collect coverage from, say, interrupts, background threads, init code. We only can collect coverage what's reachable from system call. Yeah, and the number you all were waiting for is total coverage. So we cover 250,000 basic blocks out of 3.5 million, which gives us approximately 7% of the kernel code. I think this is for x86. And doing some very unsound, but yeah, which is not very large. So for kind of, if we cover everything, you need to multiply bug numbers, say, by 14. But doing some very unsound math, I converted it to lines of code, and this gives us pretty cool 1.8 million lines of code. So we maybe have the largest kind of test case base for Linux that allows us to reasonably quickly cover like almost 2 million lines of code in a virtual machine without any hardware. Yeah, but those are not really tests, so they don't test anything. They just cover the code. And so we still need more descriptions. So Syscaller is interface aware, and it needs descriptions of the interfaces to test the kernel. And we can add all of them because it requires some expertise in the subsystem. Yes, so all kernel developers are welcome to add more. And I just show you a brief example, kind of so that you're not too scared of this. So let's say this is for floppy drive. Yeah, and this is this description actually the reason for the recent events that happened with the floppy drive in the Linux kernel. So let's say we want to add descriptions. So first of all, we say that there is a special type of FD, which is we call FD floppy. And then we say that if you open this particular file, you get instances of this floppy descriptor. And then we say that there is an ioctl on this FD floppy with this constant, and which doesn't accept any argument, and there is another one which accepts pointer to this structure, and here is the description of this structure. So you can think of this more or less as a C function and structure declaration, just with slightly more semantic information. Yeah, and the last thing is stop devices. So we have tune, we have some other, and they're super useful in covering code that is kind of not normally reachable from user space. So we absolutely need more of them. They're not useful not just for fuzzing, also for unit tests. For example, tune allows you to write very kind of handy abstract unit tests that can test incoming network paths. And if that can be unit tested from user space, then it can also be fuzzed. Yes, and that's it. Thank you.
And unfortunately, we ran out of time for Q&A. Thank you.
So can you hear me now? Okay. Okay. So the title is collaboration, unification around unit testing frameworks, and hopefully we can get some discussion around what's important around unit testing and unit testing frameworks for the kernel. So that's the goal. But since I think people also maybe don't know about where we come from, or myself in particular. Oh, thanks. Turn it on as well. Yeah. So I've been working pragmatically with the test-driven since 2001. And once I started and I call it pragmatically test-driven, that means test-driven whenever it's actually possible to do it within the time frame given by management. Because there's always a time limit, you have to deliver something within a certain time. And it's about trade-off between time and quality. So, and once I kind of started there, I've never gone back. So I always wanted to do that, to continue to be able to work relatively test-driven. So KTF, as I call it, kernel test framework, was originally conceived as K-test from testing needs that we had with an InfiniBand driver that we developed at Oracle for a couple of years. And but since the K-test name was already taken, we had to come up with something new. And initially we did this with QM and hardware simulation, and we needed to have really focused tests, because if you run something in the hardware simulated hardware, it takes forever to run even a small piece of code. So we needed to have really focused tests, so unit test became important in that sense. So when that project got cancelled, unfortunately, then I was actually requested to look into what can we salvage from that project in terms of tools, and that's how KTF became what it is. So I kind of rebranded and refactored it in early 2007, and then I got excellent help from Alan here in the front, who has added cool features to it and really kind of enhanced it and got it further on to my great pleasure. And we actually considered the name KU-unit as well, but since Q in Norwegian means cow, so cow-nit doesn't really sound that well, so I skipped that. So, and I think it's also important to know that unit testing plus continuous integration equals true. You need to really have, to get the full benefit out of unit tests, you also need to have a continuous integration system that makes sure that you don't have to fix all the bugs that other people introduce in that causes your tests to fail. Yeah. So yeah, and we have Alan has written an excellent blog entry on the Oracle blog that shows you an example of how of his development of a unit test that covers an interesting kind of simple example of how KTF can be used. So to the real topic of today, what are we really trying to achieve with unit tests? Well, in my view, we want to achieve a more test-driven culture for kernel development. And the main challenge with test-driven development is that it is, to some extent, a change of mindset. And that means that for those of us who have already seen the light, we just need to make it easy to continue to work test-driven. While for the rest of the world, we basically need to make it as so easy to use that it's kind of unresistible. So like the drug dealer approach, where you give the first doses for free, and then people get hooked, and then they start continuing to do it. So that's kind of the idea here, I think, isn't it? So I think it's about scalability of the kernel process, because kernel development process, because not all of us are geniuses. We make mistakes, and we might not understand the code in the kernel that well. So if we can kind of get to a point where we get a lot of unit tests in various areas of the kernel, it will be much easier for people getting into this, because these tests can serve as kind of assertions on the code to make it possible to understand, more easily possible for people to understand how the code works or are supposed to work, or even you can have an assumption about the code and introduce it and see if it passes, and it might fail, and then you gain some knowledge from that as well. So it's also kind of a safety net to entry. So now this is kind of the preacher preaching to the community, I suppose, because all of you are obviously interested in testing. That's probably some of the problem too, that those who really would need it, they wouldn't bother to come anyway. But I thought it would be useful to just have kind of a hands up and see if everyone agrees on some basic ideas here. So, for instance, how many of you would agree that what I describe now as a pragmatic form of test-driven development should be encouraged? Hands up. So, yeah, some 30%. Almost. Okay, that's interesting. I thought that was kind of 100%, but okay, that's good to know. How about the fact that testing tools need to be intuitive and concise and rewarding to use? How many of you would agree to that? Oh, slightly more, but not all. Oh, so it would be interesting to know why not. But okay. So, do we, with the unit test framework, do we want to cover all types of use classes, or can we introduce the API without with only covering parts of the problems, part of the kernel, for instance?
I don't understand that question.
Yeah, so to try to elaborate, is it okay to have unit tests that can only be applied to certain parts of the kernel? Or does it need to be applied to all parts of the kernel?
Right away or in future? Do you mean right away or in
yeah,
future?
I mean, for instance, drivers, is it okay, should drivers be supported? Driver testing or hardware testing?
I mean, like, if you say, like, support hardware testing.
Grab the mic behind you.
So, I feel like this is kind of a loaded question.
It is, of course.
Yeah.
That's the whole
like,
idea.
I think it's fine to, it's fine to have a unit testing suite that doesn't do end-to-end testing, right? Like those are very different use cases. Like I don't think there's really any point in trying to cover end-to-end testing, for example, because Kselftest already does a good job doing that.
Okay, so how many of you would disagree with him? Oh, some, thanks.
I disagree with the last part. Kselftest is scratching the surface as are most test systems. So.
Any other comments to that? We'll move on because otherwise it won't be finished. So, do we agree that the drivers and hardware are a big pain point in the kernel with respect to testing? How many? Oh, quite a few. Do you think it would be good to have a test framework that supports tests that cross the kernel user boundary so that you can have parts of the testing in the user LAN and parts in the kernel LAN? Yeah?
Yeah.
Yeah? Oh, hands up again? Yeah, I didn't look carefully. Oh, good. Good, some 50% or something, maybe. And I think also I will claim that one particular class of tests that's not particularly good covered today that we need to cover is tests that cannot be done easily with just one kernel. Network tests, for instance. How many of you would agree to that? Very few, actually. Yeah, that's interesting.
Well, yeah, that's because we never do that kind of testing.
Yeah.
People aren't familiar with it, so they don't know how useful it can be. Where's Mike?
Also, it's second kernel is a bit like a hardware. If our goal is mocking out hardware, you can also mock out the second kernel.
Yeah, you could to some extent mock. So mock could compensate maybe, but some tests would probably need two kernels. If you have network test, two.
Yeah, I think
so when you're
biasing it by saying kernel, well, you say more than a single kernel.
I think you're biasing it by saying, phrasing it as single kernel. It's a kernel plus other stuff. Yeah. Like there's a whole bunch of tests you could run if you had a video analyzer or a USB, something that can control USB hardware or something that did power measurement off board. So there's all kinds of tests, probably an infinite number of tests that you can do if you have additional things besides just the software under test.
Right, that's probably a better, that should kind of generalize it to that, I think, yeah. Good point, thanks. And the last bullet, how many of you would agree that if there are good user LAN tools for things, that it doesn't necessarily need to be reinvented in the kernel, or do we want to have everything in the kernel? So let's say, how many of you think that user LAN tools in general should be, if we have good user LAN tools, should we then use them as dependencies to the kernel? Or dependencies to testing or whatever, yeah? For testing, yeah? Yeah.
I would say it depends on how well it fits into the kernel and how much it actually provides. So pulling in dependency to get just some small bit may not worth it, but
yes, so that's,
benefit.
I agree with you on that. So that I think, but when there are good tools that already are maintained outside the kernel, we agree that it's good to keep it that way. Is that how many of you would agree that? Not that many. Interesting. Okay, so let's move to the discussion areas. Yeah. So I think, yeah, you know, there's something called religion that plays in some of these topics, I think. And what is really a religion? Well, it's something that's based on dogmas, which is, and the dogma is something that which one think is true, which is, we kind of assume it's true, but we don't have any proof for it. So I'm trying to be a little bit provocative here now. I don't know if it works. But we have the neat factor. I think that's a really important one. That if someone is going to use some program, it needs to feel good to use it. Or if it's a device, think about an iPod or something, how it became what it became because it was so neat to use, so easy to use that anyone could use it without any documentation. I think that what we need in the testing space is a way of making it so easy to get started with tests that it's no excuse not to do it. And we also need to make sure that the input is similar for all tests, so that you could take example tests, look at them, and redeploy them in other areas easily. And also, the output needs to be configured. Oh.
So I'm going to go back and say that unified input might be a dream, because a lot of subsystems are very different. They rely on different things. And I don't see that happening. Unified output, yes, that's really, really useful. But unified input, maybe not.
To some extent, maybe. I mean, what I'm thinking about with unified input is that the primitives to check things are similar, for instance. That you have a similar...
But if you're talking about unit testing here, then the unit can have different things as input. It's very hard to come up with commonality.
No, so I think maybe input is a wrong word. I think input to the tests. So in the assertion language,
okay,
like to put the language that we use to devise the tests. If we look at the kernel today, we have tests in /lib. We have some tests in Kselftest. We have tests spread out in some userland modules and so on. And they have very different languages in how to express assertions about what to test. If we can kind of unify and own, so I think we are moving on to the next one here, that we take in some to take ownership of the unit test namespace. I know Brendan was trying to have assert equals and expect equals, which is kind of the standard unit test primitives, as primitives in KUnit, but he was told to rewrite it to KUnit underscore assert underscore and KUnit expect underscore, which I think kind of, do we really mean serious that we want to have unit testing? In which case maybe it could be promoted to the same level as, let's say, bug or warn or some other short primitive, so that it's easy to, for those of us who have kind of a limited amount of key clicks to make before our arms are dead, that we don't have to type more than necessary. Any comments on that? The namespace issue? Sounds.
Yeah, I agree that unit tests should be easy to write and they should be concise and kind of, yeah, don't have too much typing, boilerplate typing.
And also, I think the second point, moving tests from, or taking the work of unifying the tests is something that I think is useful. And I've actually had a master student working for me or doing a master thesis where he looked at how we could convert KTF, some of the existing tests, such as the X-array tests and the R-hash table tests and a few other small tests that already are existing kernel tests. And he kind of converted them to KTF to kind of show that it's possible to do that, that the expression, that there's enough expressivity in the code. And I think doing that work, while it might seem like kind of elaborate, unnecessary work, is important, because then when people start looking at some area, they would take examples from existing code, and it's important that that code is kind of consistently doing it in the right way, or kind of the intended way. How much time do I have? Yeah. Ten more minutes, good. Okay, what I found when I tried to integrate KTF into the kernel, I found that what I call inadequate support in the kernel build system. I know that Kselftest, if we look at Kselftest, it had done quite some work to try to make it possible to even build user level or target architecture programs, and that distinction wasn't clear enough to me until I posted the patch set, that there's actually the difference between host and target in some circumstances. For us coming from the server side, it's not that, but that there's no rules in the generic build system in the kernel to build user level applications together with kernel modules for testing, because they naturally belong together in a test sense. And there's no good way today to in my view, to support having kind of similar rules in the kernel as we have for obj-y. We should have similar rules for host programs, or there's for host programs dash something and libs, but there's nothing for target programs. Because if we change, I'll postulate that if we change the config to a kernel, it's no longer the same kernel. So if we depend upon changing the configuration to build the test framework, we are no longer testing the same kernel. So really, configuration should not be needed. We might need configuration for building because we require some features for the testing itself. But in general, it should be possible to have an existing production kernel and then deploy a test framework towards that production kernel without having to make config changes. Because if we have to, then we are no longer looking at the same kernel. Yeah? Yeah. Okay.
Yeah, so it's actually one of the reasons that, for example, the distro kernel doesn't ship the Kselftest, because the Kselftest needs to the extra K configs enabling all debug options and so on, and so it will be also good if we have a Kselftest just without any extra kernel configuration enablement, so that can test the kernel, so distro kernel as is with test case. Yeah.
So you mean if you have, are you actually planning to build the Kselftest on the target system, or you want executable shipped? Is that how?
Yeah.
What are you looking at?
Depends.
Yeah, it depends.
Yeah.
So you don't have to in the mode where you have a distro kernel running, right? And then you are building self-tests on that to run. You have the Git repo, whatever. So then you don't have to, you can use your old config current config and then build self-tests. You can do that. There is nobody stopping you from doing that. Config fragments came in partly because in CI environments, they have variations on configurations. So it made sense to enable configurations and giving some control over configurations options. So that's how config fragments came about. To be able to have some control over the config fragments. Is that correct, Dan? Right. So so that's why that's a tweak to support some of the CI environments. But you can build a default with the current config.
Then what's the necessity of having the separate kconfig for each test? Can we have just one I built Kselftest, and for all the modules or the built-in drivers that I built?
Okay.
Yeah, you can do that.
Tim is very eager back there.
So I want separate config fragments per test because I want to use config fragments not to shape the software under test, but to shape as information for the test scheduler.
Yes, so that's why maybe it needs to be a separate dimension.
Right, it's a separate operation. So like I'm doing mostly product testing, and so I never change my kernel config. Well, I use the kernel config that the product guys chose, right? So I'm not in a position to go modifying my kernel configuration. So I'm only interested, what I would use it for is finding the tests that apply to my kernel that have those options enabled already. So I assume that
yeah, that's exactly the same use case that I'm kind of thinking of. Box.
I was just suggesting we only have a couple minutes left. I'd like to hear about the proposed collaboration integration thing.
Well, okay. So this is it's more of the same here. So it's not really. I mean, I feel that this is collaboration, unification. How should the ideal unit test system look? That's what I'm kind of trying to get at. So we've been touching upon that. So I think tests really are different from production code. That's what I've alluded to with dimensions, that we need to have proper support from the kernel build system to the test space, and that's going to be different from production code. Right now, if we look at, if I want to run the X-array tests, I have to change the configuration for that test code to be built, and it's also positioned inside the kernel tree below kind of this one of the paths that where other actual kernel production kernel code is, and it shouldn't be. It should be located under tools testing somehow, where maybe everything could be under self-tests logically. So I mean, the test frameworks, everything that has to do with tests, and it should be made kind of orthogonal to the code itself. So more than one dimension. And also, I think one important aspect of testing that's not covered by having everything into the same kernel, but that could be covered by kind of the same approach as compiling modules, is that it's possible to, even though everything might be in one kernel repository, that it's possible to take that whole shebang and compile it against another kernel, so that it can still be used to test an older kernel. Because one important test case is we have developed, let's say we have developed a lot of tests, fixed a lot of bugs in the recent kernel, and then someone has a production kernel and they would like to see what bugs are we exposed to in that production kernel. Then it should be easy to take whatever test logic exists in the kernel, recompile it against that kernel and run the tests against that production kernel without changing anything.
Yeah.
Maybe you might not be able to run all the tests, but at least the tests that would work with the support that is in that kernel. We out? Okay? That's all I got to do, so thank you.
In the meantime, if someone could help with the notes, it's been one person doing a really, really heroic job. Should I just start picking up people out from the audience in random?
I'll do it.
Thank you.
So this is my usual yearly talk that I do at either Kernel Summit. Sorry, Mike. So this is, thanks for having me. This is a usual talk that I do once a year, talking about the state of kernel self-test and find out what we want to do and what we can do to improve it. So 3.17, that's when we started kernel self-test. That's 5 years ago. We had 15 targets in the makefile. The way kernel self-test works is you have a bunch of directories. This is written by developers for primarily for their main use. We are stretching it to use it, run it into users by users. So there are some challenges, but some of the challenges that you're bringing up. But since we started 15 targets to now we're up to 70. I just counted how many directories we have. Usually directories means each subsystem type tests, and then under that you'll have multiple tests. So you're looking at, you have a major target, and then under that multiple test suites. So you might be looking at probably upwards of 1,000 tests. So these are I'm not going into too much detail on Kselftest itself, partly because I want to use this session to talk about some of the CI related improvements we could do and clarify how to improve some of the CI experiences. So I'm not going into too much detail. So there are 3 different kinds of use cases for kernel self-test. One is rev-matched. That means You have a development system, you are running tests on your development system while you are doing kernel development, essentially. So you're testing your kernel, and you might be testing just running a subset of tests even. So you'll build a kernel self-test from the same repo, and then run tests on that. So that's the one I'm showing on the top left. The second one is stable release testing. Stable release testing, you can have a couple of different modes. You can use the mainline latest on stable releases, or we'll get into more of that discussion a little bit later. Or you can rev match it similarly. So the third variation is a lot of the CI, Linaro folks do that, kernel CI. They will compile, and they have a development system that they will build, and then they have a target system. So I'll kind of give a current picture of results from kernel results from. Do you want to do your tables at this point? Sure. Okay, yeah. Show your tables, and then we'll talk about some of the other issues. So at this point, I mean, if you want more information on the Kselftest, I can go into it. I don't have slides, but I can go into it if you have any questions. You have one, right? You have a question. Go ahead.
Yeah, so there, as I said, just like in the previous talk, that how can we encourage that, including the Kselftest enablement on these distro kernels?
How do we want to include them? I guess that's the question.
Right. So that one of the things that is, as I mentioned, that the kernel configurations, we do not explode the kernel configuration. And so there, yeah, that's, if the Kselftest works always with the distro kernel configuration for the drivers or the base configuration, then we can just enable each and ship or just build, and that's some people using that or testing in the build infrastructure and so on. But currently we do not do that because we fear that we will hit the kernel config mess somehow.
So it's, I do this on my development system, and I use distro, whichever distro I'm running on it. I use the distro kernel and then make Kselftest, and it will use the distro, your configuration.
Yeah, I think, Takashi, is your issue is that Kselftest needs some configs turned on that the distro kernel hasn't enabled. So to run Kselftest requires is set up to require options to be turned on, and it doesn't. But Takashi wants to test his distro kernel, which does not have those options on. So he needs Kselftest to run cleanly. It's not about building; it's about the target system. Getting Kselftest run cleanly on a system where the configs are disabled, if I understand correctly.
So is that what you're saying,
yeah,
that you want to, okay.
Yeah, just one of the concerns that Kselftest is guaranteed to work even with the limited kernel configurations.
That is the goal. That's what we keep working towards. So there is, so that's why if the feature is not supported, tests are supposed to do one or two things. That the unsupported, which is usually a skip, they do skips. So we have gotten there. I can't say that all 100% of the tests that should skip do skip. That's not reality. Partly because we keep adding tests every single release, right? And some subsystems add more tests than others. Networking adds tons of tests every time. So we do miss some things on occasion. So.
I have a follow-up question on that for you, Shuah, before. Do tests skip for configuration missing? Do they do configuration detection?
The configuration, the feature detection sometimes. So there depends what kind of test depends what kind of test it is. We have a mix of binaries and we have a mix of shell scripts. Shell scripts go, in some cases, try to load a module to test. If the module isn't built in, they will skip the test. So that's one variation. The second variation is they do go and look for a config. If it's a shell script, it goes and looks for a config option. So if it's not enabled, it will say config option is not enabled, it'll skip, right? The third variation is system calls. I saw your hand up, I will get to it. Let me just finish. So third variation is the feature itself, right? For example, you might have I'm just going to say system call. So you have a new system call, new flags are introduced. You make a support for new flags got added. So this will be a runtime determination, meaning you actually make the system call, and you either get invalid or unsupported, whatever return value. That return value is interpreted, and then it'll say the kernel doesn't support it. It's a skip. So there's multiple variations of these skips. So what are you the one you are interested in is, I guess that's the thing. So it's a complex set of checks that are made on the features. So some of the shell scripts do check config options, and binaries don't always. They work in a different way, because we have a bunch of things that we load. Modules get loaded. Test modules need to be loaded also. So I think my goal is, this is why I do these sessions. But as people come up and say we want to run those tests, I want to be able to make that happen, obviously with your help, because I won't be writing all the code. So you will be helping me, helping Kselftest get there.
Is it a good time?
Yeah. Is that? So do you have a follow-up question, or do you? Okay.
Hi. Kind of question about it's kind of multiple questions, all similar, same vein. Are distributions packaging Kselftest and installing on their systems today?
I don't believe so, right? That's the question. You're not, right? You're not.
And,
part, okay.
And if distributions did do this, do you think use of Kselftest would become more prominent? Is that what you're trying to push?
Yes and no. We are using it in primarily in our integration test cycles currently, right? If I think you are interested in having that tested in distros, or you want to increase, right?
Part of my problem is, I'm kind of leading an effort inside Red Hat to kind of get developers to write more tests. And a lot of questions I have is, okay, I have a test, I have a shell script right in my hand, but I don't have a framework to wrap it around. So they're always asking, what framework do I use? A lot of times you push them to LTP. It's a good, stable framework. It's, a lot of people can help you with that. A lot of times lately people have been looking at self-test, like, well, is this a better option? It's got a framework, it's inside the kernel, kind of use that. And I thought about if we package that and push it out and wrap our test harness around it, would that be useful to push? I'm just trying to wrap my head around about.
So I think it would be useful, because the pros of the kernel self-test is, the reason we kept it with the kernel sources is because that we can ship the kernel with the tests that test the kernel as we add new features we add tests as well, which is what we do.
Well, more important is, my more concern is, for the rel kernel, a lot of times we push things out, things are broken, you have to revert it. So reverting the patch that caused the problem along with the test case is usually a big win too. So that's why I like your model.
Right. So but having both in the kernel helps you with that model, right? That's what you're saying. So that is the plus point of that, and then the negative with having, because we are actually moving tests and the kernel at the same time. So right. So the tests are going to be broken. It's an expected thing because RC7. So you are going to see that. So you will have probably kernel bugs and as well as test bugs. So those need to be fixed as well. So that's the reality of it.
So who would own those broken tests? Would it be the subsystem maintainer? Would it be somebody else?
Well, it's the same kernel development process that happens, right?
Right.
So, yes, whoever writes the test fixes it.
I mean, what I'm trying to get to is that if you are sending a patch in that's breaking the self-test for that subsystem, you probably want to be fixing that self-test at that point in time. And therefore, I mean, if there is a bug in the test is broken, that means the process is broken.
So let's address that in a bit. I mean, just hang on. So to answer your question, I think having running Kselftest in distros will. I think this Kselftest enhancements will happen. Like for example, you might have. We have pulled in a lot of tests the same way. Several developers had tests sitting in the Gits, and then we included them in the kernel, and we are running them now. BPF came in that way, Futex tests came in that way, timer tests came in that way. So we have kernel developers, if they had their tests sitting in their private Gits, they brought them in. So which is good, right? So I think that if distros get involved, I think Kselftest all of a sudden will have more tests. I want to see that. What I'm saying is there are some pain points with that approach as well. Meaning, when you're coming in, you do have to expect, because the developers are writing new tests, and then those tests might not always behave. I mean, there aren't test bugs, but expectation, right? Dan will get into this a little bit. Dan has more experience on that. What happens is we expect tests to skip gracefully, right? Those are the kinds of bugs I'm talking about. So they might not happen. We find them in Linux Next. Just like in every other kernel bug we find, integration cycle, we do find them. And some tests, depending on the cycles of when maintainers choose to, so the self-tests flow a little bit differently. I maintain the framework, I maintain the tests. However, individual tests go through maintainers' trees sometimes, if they have dependencies. For example, there is a new feature that went into a area, for example. So those tests, new tests, they go through trees for good reasons, because if we try to, so that's how it's working right now. So because we are encouraging, I want to kind of say, hey, let the tests get in. If there are dependencies between trees, let's work it that way, and we work these things out in the Linux Next. So as a result, what happens is, close to the merge window, depending on when the content gets into Linux Next, sometimes we don't find them soon enough. So it might be that we are finding them after release comes out, and then just like last minute bugs that get found. So they end up going into .1 release of the stable. I'm thinking you have a question, right? No? Yeah, go ahead.
Kind of comments. So I'm a kernel maintainer for Ubuntu. We run a subset of the self-test as part of our release testing. And like one of the things related to just what you were saying is the more that the tests can remain coupled to the commits that have the changes they're testing, that's a big help, because one thing that we run into is with stable updates, they might backport a fix, but the test needs to change too, and that doesn't get backported, and now our tests are failing. So the more that we can keep those things together, that's a big help to distributions, I think, to being able to use these tests. And the other thing is, like with the, I guess what I would like to see is that if we could have more of a CI type of testing for Kselftest and Linux Next, so that when we get to RC1, hopefully we don't have Kselftest failures that are just because the test didn't get updated, or somebody actually introduced a regression and they would have caught it if they had run the Kselftest.
Right. So that's a pain point for me as well. So I am actually furiously after the merge window sometimes, and once the RC7 or RC8 comes out, I do find Kselftest problems, and I'm looking to fix them.
So, right, from a maintainer's perspective, like if I do self-tests, or well, not if I do, I do self-test, and there's a requirement that if something goes to the tree, there is self-test attached to it. But it requires me right now, and this is related to what Seth has been saying, it requires me right now that before I accept something into my tree, which I obviously do, then I compile all of the tests that I have added before, and I run them, and I check if everything still succeeds, right? But this is only for my tree. I'm not cross-checking what other trees are going in. So if Linux Next would, for example, tell me, by the way, one of your tests is failing, that would be really valuable.
Okay. So that would be something we can look into adding, definitely, if that helps. Yeah. Is what? I mean, go ahead.
Oh, sorry. I was just wondering. You know the way we have this convention, when you fix a bug, you have that fixes tag that refers to where the bug was introduced. If you had a tests tag that referred to when the feature was added, or that would be a way to build a relationship between when you add the test, you have that tests tag in the which references the git commit with that feature, and then you could use that to figure out which tests to run, and you could also use you could understand much better what that relationship is between when the tests are added and when the features were. Even if the feature was added a long time ago, that you could have that relationship, and that would help people figure out, okay, this feature is here, and that might be useful.
We'll have to look into that. The test files, and Dan is trying to. So to answer your question about Linux Next testing, CI folks do that. Linaro, they have been doing that. They do report. They send it to Kselftest. So I'm going to have Dan talk.
So I have kind of a user experience here. I work at Linaro. My name is Dan Rue, and I work with LKFT. We do continuous integration of Linux trees, especially the upstream Linux trees, mainline, next, and stable and LTS branches. And we've been running Kselftest since we started about 2 years ago. And so we have a lot of experience trying to get Kselftest results. And I'm here for feedback on how we're running it, because in some cases we're running it wrong. And I'm here to give feedback in terms of how things that we think would improve Kselftest to make it more approachable for, like the distro concerns are one of the main ones. So we have approximately 10 different boards that we run on. We run a variety of tests in addition to Kselftest. So this is just background LKFT slide. This is the like aggregate number of tests that we've run over time. So we started about 2 years ago. You can see we've run, I guess you can't see, it's 60-some million tests in that time on the stable trees, mainline, and next. So this is kind of the meat of it. This is a snapshot of our results of Kselftest. On next and mainline, we run the in-tree version of Kselftest, so it matches. On stable and LTS branches, we try to run the latest version, the latest stable release of Kselftest. So today that would be something like 5.2.11 or maybe 12 now as of this week. We don't rev that automatically, and so some of the results don't actually show that if you go into our database and look at our results. But that's our policy. We try to run the latest stable against all the older branches. This is one of the more controversial parts of what we're doing. A lot of kernel engineers think that's the right way. A lot of kernel engineers decidedly don't. So we kind of like it because we get a lot more tests run. The experience isn't as good because we get a lot more failures. Yeah, so let me just describe this graph, and then we can talk about it a little bit. But so this set here, the first set, is 5.3 RC7, so this is recent data from last week. And you can see the numbers of the rows here are the different environments that we run in. And you can see the numbers of passes we get. These skips are Kselftest emitted skips, so a test decides that it can't run for some reason. Skips are awesome. Failures, and you can see the failure counts. And then the second set of data there is 4.9.190, running Kselftest from 5.1 release. That just happened to be the data I had. And then the last column, the last set of data there is 4.9.190, the same kernel, but using the in-kernel version of Kselftest. And so you can see the difference in quantity of passes and failures. We get about twice as many tests running successfully if we use the latest version of Kselftest. But we also get about 10 times the number of failures as we do because all of the new tests that have been written since then that don't apply to the kernel, most of them fail. It would be nice if they skipped.
I just have a quick question about the fail counts. One thing I've noticed when looking at Kselftest, and this has come up when I've been writing my own self-tests, is that a lot of self-tests are bought early. Whenever, so for instance, you have one suite, you have one binary that is doing 50 tests. If one of them fails, it'll abort early and it won't do the rest of the tests. This happens in quite a few. There's the one for MFD and a bunch of others that do this. The question I wanted to ask was, is there a plan to sort of push for doing it in like a more traditional way? For instance, with other tap-based frameworks, they usually, you run all of the tests and you just output which ones failed rather than having the first failure causing an error. And I guess the question is the failure number actually an underestimate, given that in many cases the tests will fail early?
So I believe our parsing, Anders, maybe you can correct me if I'm wrong, rolls up the results. So each set of tests shows up as a pass or a fail for us. Is that right? Yeah. I'm getting a nod. So now it would show up as a failure.
So to answer your specific question, it depends on what the test author decides to do. Because, but if that is something, we can look into improving the framework.
Okay.
So to Dan and Anders, they have done a lot of work helping improve the skip parts. Actually, they either gave me feedback, so I went and did framework enhancements to make their life easier. So we have done with the collaboration that I have with Linaro folks, we have done a lot of improvements. So we keep talking about it. As I understand their pain points, we keep improving. So if that is something we can do, that it is up to the test developers. The way you're writing tests, right? Yeah. You're actually I'm seeing your patch series. Yeah. So sometimes what happens is the developers are doing two things. They are doing their kernel feature and are also writing tests, and then in some cases, I'm trying to fix this as well. Some cases, by the time I come and comment on the framework, I have to do that myself. I might be late giving comments also. So there is all of that happening too. So I think the goal is really when you write a test, send a test. The test should skip gracefully, fail gracefully, and cover. It's also Kselftest document. If you look at it, it clearly says run as many tests as possible before skipping or exiting. You skip and keep going, but run as many tests as possible. If you have 90 tests to run and only 10 cannot be run, don't abort early. So the only exception to that would be if there are even the root case. Some tests require root access. So my recommendation is write the test such that you are still going ahead and running rest of the tests, but just skip the ones that need a specific feature. So that's the recommendation.
Yeah, I have some suggestions, but we can talk about that later because it's a bit technical. But yeah, I agree with the general point.
Right.
Why do you say that?
The question was
the
that...
question was, is it on the radar?
I'm sorry?
Oh, sorry, mine or his?
Oh.
Mine. It was, is it on your radar effectively? Because if a test fails early, the fail count you have there will be an underestimate. It was my point. As in, are you aware of that, and is there a plan to work on that? Was the general question.
Why do you say that the skips are awesome? So consider all tests as skips, and LKFT will say that everything is good, but you actually didn't test everything. So what I'm getting at is that the CI actually need to solve the reverse problem of distros. You have a set of tests, and you need to figure out what is the configs, what are the user space packages you need to run all of the tests. So that's this seems to be one of the major missing features in the case of tests. And the CI is kind of the main use case for any test suite.
I like skips because usually it means the test is, a good skip means that the test is inappropriate to run. We're running on a lot of small boards with limited memory, limited capacity, or an architecture that isn't supported by the test. And so in my mind, a lot of times those fail. A config doesn't exist. A config wasn't built in because sometimes the config fragment is missing from Kselftest. The test will fail. It would be better if it skipped.
Well, it will be better if you will have the config that is needed to run this test.
Right. But if it's not possible, there are tests that aren't possible to run. There's an x86 test, and I'm on an ARM board, and I'm running all the tests. So the way we run is we use the generated, Kselftest generates a run file for you that is like a script that iterates through all the tests, and that's how we run it. So we run all the tests together. It's not sophisticated enough to deal with the board at the time of build in terms of the environment that it's running in.
So all the skips are kind of inherently can run on this hardware?
I doubt it.
So there are still skips that can...
So the skip means that if the kernel the test is running on, the kernel doesn't have the support for the test to run. So that means, Dan is point of view, he's looking at it from the point of view of his test systems, right? And they don't have, not all of the Kselftest run on those. He knows that. So he's saying skips are good from his perspective, that they are not reporting false failures or false. From that perspective, it's a good thing. However, skips aren't coverage. If you're looking at the coverage angle, skips aren't doing any coverage. I mean, having 75 skips and 25 passes, it says you only ran your either two things. One is your test system can only run 25 and it ran them, right? And the rest 75 are skips because it couldn't run, so it correctly reported skips. Correct? And then
in the case of running a newer version of Kselftest against an older kernel, though, I would expect a lot of skips because we run this on 4.4. So if you're running Kselftest from 5.2 against a 4.4 kernel, there's a lot of features that it's testing for that don't exist in the kernel.
Classic examples are syscalls that are not implemented, for example, on some architectures where we skip self-tests.
Right, exactly.
So I'm a little concerned now that we are just talking about tests that, or running a large set of tests and some of them will fail, and not really thinking about what tests did pass before a change and what did pass afterwards, which is kind of the CI idea.
We have that data.
I don't. So okay, there's a couple things. I wanted to address the point earlier about running our reports on Next. We do send a report to the Kselftest mailing list that iterates all of our failures that we get. It's not like sophisticated enough to figure out whose failures they are or anything like that. But there is a report going out to the Kselftest list, and we'd love feedback on that because I don't know if it's useful, and I don't have an example here, but you can see that on the list.
So I wonder, for example, for files that have a dedicated maintainer's entry, for example, so that show up in the maintainer's file, there's like this self-test is maintained by this guy.
Yeah, we don't do that yet.
Send him a mail.
Yeah, well, so what's missing... What's missing is metadata associating the test with the code. And that was something that interesting that the CKI guys apparently have, and CKI project has something like that. But so that's something to consider. But I mean, can't we like within the maintainer's file, like the maintainer for whatever area of the kernel, put the self-tests for that area of the kernel under their entry in the maintainer's file?
We do that. Yeah.
Exactly. This is exactly what I did. So I have like everything that's under a specific keyword in the tools testing self-test blah 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 directory has an entry, and that's basically how it should be, because then it's also guaranteed that the maintainer sees additions to the self-tests. So if you run get maintainers, then he or she would be CC'd as well. And then it's also a good thing if the maintainer can take it through their tree.
So that's what we do, right? I mean, that's how it happens.
This is what I do. I never knew, but for example, I don't know if this is documented anywhere, but I wasn't sure if I'm stepping, for example, on your foot because I just send all of the self-tests directly.
Right. So the way I would like to know about it, that you're sending the tests, because then I can look at the framework and then avoid these kinds of things like should it skip, or I do review those. So one of the reasons I let patches flow, I have a slide somewhere that I show how the patches flow. The reason is that I want tests in there. I don't want to be the blocker for, block the flow of tests.
Right.
So that's okay. What you're doing is fine. So the one thing I would like to know is if you're sending tests, I would like to know about them, because then I can review the framework, right, to avoid. And the second point is where, Dan, one thing you guys can do is key off of the maintainers, get maintainers data, and CC more. Then we could run into spam too. So
I mean, based on what he was saying, if you're always, can't you just add an entry into the maintainers file for kselftest saying when you do get maintainers .pl, whatever, it automatically CCs you, and it makes it a little bit easier so you don't have to ask people to CC you.
So, well, I do actually. That's how it works. But in some cases, oddball case, I have to figure out some things aren't working right. So I don't see some patches. So.
Mike.
Oh, sorry. I believe, correct me if I'm wrong, I believe that get maintainers will, if there is a more strict match of a file, it will give you that maintainer rather than the directory one. Or does it give you all?
It gives you everything, but because get maintainers will copy in the world half the time, people will often do a manual filter on it. For example, if you've got the thing that looks at the git log turned on, you'll often find you're CCing people who do lots of spelling fixes or whatever, and they don't need that noise. So people do filter it by hand. No, you shouldn't really trust get maintainers to do things automatically.
That's actually why it's important that a self-test associated with specific subsystem or whatever has a dedicated entry, because then it will show up in get maintainers output as maintainer, and then people will usually at least CC those, I think.
So that's kind of what we have.
Most
new tests that get added, test maintainers add their tests. But we seem to have, reporting. I have been asking Dan reporting to be improved a bit too. So we'll figure something out in reporting for sure.
And one of the things we found with kernelCI, which I suspect is also true for LKFT, is that having a manual step where you go and a human goes and tells the person that they broke the thing helps a lot with people actually paying attention to the results. If they're not, if you've got something like a bisect, it's really easy to get people like Guillaume implemented for boots. It's really easy to get somebody to pay attention. But if you just send somebody a mail, or if an automated system sends somebody a mail saying there's a breakage somewhere, it's a lot harder to get a response than it is if you've got a human going, there's a breakage somewhere. There is still a breakage here that's been here for a week, you know.
Right. So that's what I told Dan and Anders. Flag me. I will go figure out how to get that happen. Because I am not, some of these failures, we talked about it. We had a meeting, you know, we sync sometimes. So yes, that's exactly what I told them. Because what happens is these automated reports come in and they get ignored for the most part. And then also, even if we did go to picking up get maintainers and reporting problems, it could be viewed as, if there is too much volume, they get ignored. So that's another thing I already know. We're out of time. Looks like, right. So the question, I have another session in the kernel summit. The thing that Dan, I am looking to make a recommendation because it's becoming difficult for Dan and Anders and Linaro test farm. When they run the tests, they're trying to figure out what's the best recipe. Do they want to rev match? I'm going to make this quick. That's the outstanding question. Do you rev match the kernel and self-tests, or do they run latest stable on older stables? There are pros and cons to both approaches, so we have been talking about it, and I have said for better coverage, use latest stable, and now I'm beginning to think based on the pain, the issues, painful, well, it's been pain for them. So I'm saying, well, use your judgment on how much pain you want to take, right?
We definitely rev match because we've had too many problems. If it's not like even if you take 1.5.2 and a newer update to 5.2, you can have breakage just between that SKU. So we definitely have found that rev matching is the only thing that seems to be reliable.
Right. So that's where I'm coming to. At one point, it made sense because the graph I showed you, 3.17, we didn't have any tests. Between 3.17 and 4.4, obviously we have more tests. It would make more sense to run 4.4 tests on 3.18, but when you are coming closer to like between 5.2 and 5.4, you have diminishing results. Your coverage doesn't go up. You might have more skips, but looks like we're out of time. So please come get me in the hallway.
All right, thanks everyone for coming. Thanks, Shuah.
I want to say a special thank you to Major for doing all the notes. Thank you for sticking up for us.